Good afternoon, good evening, participants. South African time right now it's 16:30, and I understand where our speaker is at Montreal. Is in the morning, is around 9:30. You are all welcome to this session, which is the third keynote address of the day. And our speaker for this session is Professor Laurence Levasseur. We are very much privileged, Prof, for joining us in this session and for accepting our invitation and to participate on our online conference. I think this morning, when we did the opening, Dr. Adams also acknowledged your participation for this conference. We really appreciate your time and effort for making our conference of this year a success. Let me also welcome you and welcome all the participants who have joined us for this session. And then the topic that you're going to be presenting to us is strong gravitational lensing and machine learning in the era of large sky surveys. And just to give the background of who Prof is, Professor Levasseur is an assistant professor at the University of Montreal and associate member of the Montreal for Learning Algorithms, where she conducts research in development and application of machine learning methods to cosmology. Prior to that, she was a Flatiron Research Fellow at the Center for Computational Astrophysics in the Flatiron Institute and CAPIC Postdoctoral Fellow at Stanford University. Professor Lawrence completed a PhD degree at the University of Cambridge, where she worked on applications of open effective field theory methods to the formalizing of inflation. She received a BSc and MSc degrees from McGill University. I think through such, let me welcome you, Prof, and over for you to give us your presentation.
All right, thank you very much for the introduction. It is a pleasure to be here, and I'd like to thank particularly the organizers for inviting me and for making it possible for me to do this presentation remotely. I know it's a huge challenge, so I really appreciate it. So like the title of my talk says, I'm going to be talking about some recent work that I've been doing using machine learning to do the analysis of strong gravitational lensing data. So before I get into the more machine learning part of my talk, I'm going to give a brief introduction about strong gravitational lensing, because I realize that not everybody in the audience is an expert. So strong gravitational lensing is basically the formation of multiple images of a distant source due to the deflection of its light rays by the gravity of some intervening structure. So let's say that here we're on the Earth and there's two galaxies, one right behind the other one. So as the light rays of the background galaxy pass near the foreground galaxy, they get bent. And so they come to us from different angles. And so as a result, here on the Earth, we see multiple images of the same background galaxy. So it's a little bit like looking at the fish from the corner of a fish tank. If you've ever noticed, you can see multiple images of the same background fish. See, here's Mr. Mango demonstrating this effect. So as he comes to the corner of the fish tank, he can see two images of the same fish. So this is very similar to actual images of strong lenses that we see in the sky. So here what we have is two images of the same background quasar in blue due to the deflection of its light rays by the gravity of the foreground galaxy in orange in the middle. So here's another example of a strong gravitational lens. So everything that you see in this image is a galaxy, but then slightly to the right, you see that there's this blue galaxy whose image is wrapping around a central orange galaxy. So this is the gravitational lens here. And that feature of forming arcs like that is very common in strong gravitational lensing. It's because of the geometry of the lens. So you can actually reproduce an effect like that at home with a wine glass and a candle. So I've prepared this little video to show you how to do that. So first you need a wine glass and also a candle, and it also helps if you have a little bit of wine and also a buddy to drink with, so that you don't end up drinking alone. So if you dim the lights to make the atmosphere more romantic, as you pick up your glass of wine to take a sip, you can see that through the foot of the wine glass, you can see that the image of the flame of the candle starts to wrap around the foot of the wine glass. So this is very similar to actual images of strong gravitational lenses that we see in the sky. So with this analogy, the foot of the wine glass is the foreground galaxy who is distorted the image of the background galaxy, and the flame of the candle is the background galaxy whose image is getting distorted. So this is what gravitational lensing is. So what can we do with gravitational lensing? Well, we can actually do a lot of different sciences. So first, we can use it to study the background galaxy. And the reason for that is that strong lensing magnifies images. So we can basically use strong lensing as a cosmic telescope to study very distant sources that would be otherwise below our detection or resolution limits. So basically, we can use it to study, for example, galaxy formation at very high redshift in the universe. We can also use strong gravitational lensing to study the lens itself. So that's because it's the gravity of the matter in the lens that's doing the distortion. So we can use it to map out how matter is distributed in the lensing galaxy. So and that's particularly useful to do things like studying dark matter, because it's the gravity of the matter that's doing the distortion, regardless of if it emits light or not. Another thing we can do with strong lensing is to use it to do cosmology, and more specifically to measure the Hubble constant. And the way that this works is that if we have a background source that has some time variability, so as the light travels through the different paths in space-time to form the different images, those different paths can have different lengths. And so that time variability in the background source is going to show up as a time delay between the different images. So by measuring that time delay, and combining that with a measurement of a lens model for the lens itself, then we can use that to infer the value of H0. That's a very important cosmological parameter. But then it doesn't matter what the science that we're interested in doing, we need to be able to extract whatever information we want from images of strong lensing. So it turns out that it doesn't matter what's the science we want to do. If we want to do anything with strong lensing from images, we need to be able to do two things. First, we need to be able to infer what's the true undistorted image of the background source. And then we also need to be able to map out how mass is distributed in the lensing galaxy. So it's a little bit like looking at somebody through a funhouse mirror and asking what's the undistorted image of the person and what's the shape of the mirror. So to see why these two things completely determine a lensing system, we can look at a slightly different but related problem. So if I give you the problem basically of simulating the distortion. So if I give you the image of a person and the shape of a mirror, it's very easy to simulate the distortion. All you have to do is put them through the simulator machine. So what that does is that it takes the shape of the mirror, and then from that, it calculates the deflection field. Then it applies it to the image of the little boy, and voila, we have the distorted image. So the problem is that when we have real data, we neither know what's the undistorted image of the person, nor do we know what's the shape of the mirror. So basically, we don't know what's the inverse function of the simulator. So to go around that problem, traditionally what people have done is that we basically use multiple different combinations of images of people and multiple different combinations of shapes of mirror until we manage to produce a simulation that looks a lot like the observed data. And then once we manage to do that, we conclude that it's very likely that we have the right person and the right shape of mirror. So this is called maximum likelihood lens modeling, because in order to compare the simulation and the observed data, we use a likelihood function that we try to optimize. And it's really that optimization step that causes a lot of issues with strong lensing modeling. So the problem is that the likelihood function that we're trying to optimize is very, very complex. So it's very common for optimizers to get stuck in parameter space. And then at that point, we need to go back and reinitialize the optimizer somewhere else in parameter space. And then on top of that, the likelihood function that we're trying to optimize, the likelihood function itself is very expensive to evaluate. So it's not unheard of to need, for example, 2 million CPU hours to do the analysis of a single strong lens. So it's a very expensive problem. So because of that, like I said, it's a very expensive problem in terms of computational resources and also in terms of human resources, because it's in need of constant babysitting. So up to now, this has not been such a huge problem because we only know of a couple hundred strong lenses altogether. So even though it takes a lot of time to model every one of them, there's not so many that it's been a huge challenge. But then in the coming years, with LSST and Euclid and WFIRST, which are big, large-scale new observatories that are going to come online in the next decade, we're expecting to discover about 170,000 new strong gravitational lensing. So first, this is really exciting because with such a large sample of strong lenses, we're going to have a lot of statistical power to do all of the interesting science that we want to do with strong lensing. And it's also super exciting for another reason. With such a large sample, it's very likely that we're going to be able to find a lot of very rare events like lens supernovae or strong lens that have been on multiple planes. And so it's really an exciting time to be doing strong gravitational lensing. But then the problem is that how are we going to analyze 170,000 new strong lenses? If we assume that it takes about 3 days to do the simplest possible model of a single lens, it would take 1,400 years of a person's time to finish the analysis of all of the LSST sample. And that's if the person doesn't eat or sleep or have weekends. So clearly, we need new analysis methods. So this is what motivated us to look into machine learning to solve this problem, and more specifically neural networks. So if we go back to the slide of the little boy in the mirror, the problem that we had, if you recall, is that we didn't know what was the inverse function of the simulator. So what we thought we could do is use the fact that neural networks are universal function approximator to basically approximate that unknown inverse function, and then directly go from the observed data to the parameters of interest using the neural network. And this way we would bypass the need of doing all those simulations that made the process very, very long. So more specifically, what we've done is that we've trained a specific flavor of neural networks that's called the convolutional neural networks. So I don't think I need to give a very lengthy introduction here, but just very quickly, what convolutional neural networks are is that they are specifically well adapted to do the image analysis. And the way they do that is that they take some image as an input, and then they convolve it with a bunch of filters to produce some output of interest. And then the key here is that the values of the filters are not fixed ahead of time. They're learned through a process that's called training, where you show the network a bunch of images for which you know what the real answer is. So, and then what you do is you try to find the values of those filters that minimize the difference between the output of the network and the true answer that you know. So in our case, what we wanted to do was to input telescope images of strong lenses in the neural network, and then have them process those images through multiple filters, and then output, basically do a regression problem. So output the values that describe how matter is distributed in the lensing galaxies. So things like the mass of the lens, its ellipticity, its angle, its position, so things like that. So we trained the neural network with simulated images, and then once they were trained, we tested their performances on 10,000 new simulated images, and also 9 real images from the Hubble Space Telescope that I'm showing here. So this is what we got. So here what I'm showing is on the x-axis, the true value for those parameters, and on the y-axis, it's the prediction of the network for different lensing parameters that we were estimating. So ideally, if the network was perfect, all the data would fall on a diagonal line. So here what I'm showing is like the faint blue points are the 10,000 simulated test images. So there's so many of them, and they're so clustered together that I also am showing the 65 and 96, so sorry, 68 and 96 inclusion regions in dark blue and light blue. And then 9 markers are the 9 real images from the Hubble Space Telescope. So what we see is that we have a very good way of estimating the parameters of strong lenses. But then the key is that this is actually 10 million times faster than with traditional maximum likelihood lens modeling methods. So basically, instead of taking 1,400 years to finish the analysis of all of the LSST sample, it would basically take just half an hour on a laptop. So this is a pretty big improvement. But then if you're an astronomer, the thing that you're most interested in is really to see something like that for every one of those lenses. So basically what we're interested in is actually knowing what are the uncertainties that are associated with every one of those parameters that we're estimating for every one of those lenses. So basically we wanted to know if it was possible for neural networks to also estimate their own uncertainties over the parameters that they are estimating. So to answer that question, we had to look into what are the sources of errors in neural networks? So there's basically 2 sources of uncertainty. The first one is called aleatoric uncertainty. So it's basically the one that comes from inherent corruption in the data. So things like noise or blurring of the PSF, and it makes the true values of the parameters inherently unknowable. The second source of uncertainty is called the epistemic uncertainty, and it comes from the fact that we're using the neural network itself as a model. So it's the error that comes from the neural network. So these things that could make it worse are things like not having an architecture that's complex enough to capture the complexity of the data, or having insufficient training data, or things like that. So in order to capture the first source of uncertainty, what we thought we could do is that instead of having the network output a point estimate for every parameter of interest, we could have it output basically a full likelihood for that parameter. But then the likelihood could be very complex, so we can approximate it by an analytic function, an analytic distribution, and have the network output the parameters of that analytic distribution. So if we assume, say, a Gaussian, then instead of having the analytic output a point estimate for every parameter, we would have the network output the parameters of a Gaussian for every parameter of interest. So this is like in the case of a Gaussian, there's two parameters, a mu and a sigma. So we could do that for every parameter that we're interested in. But then, of course, the neural network itself can make errors on those values of mu and sigmas. Even though we have a distribution, there's still that the distribution could be uncertain at some level. And so to capture that source of uncertainty, we had to look into epistemic uncertainty. So for that, we used something to capture this. We used something that's called the Bayesian neural network. So in a regular neural network, the values of the weights, so these are the values of the filters that I was talking about before, have fixed deterministic values. So it means that every time we put the same image to the neural network, we output the same value. So even though we output the distribution, it's always the same mu and the same sigma. So we always output the same distribution as an output for a given image. But in a Bayesian neural networks, you replace those fixed deterministic values by some probability distribution P that have a free form. And then through training, what you do is that you try to learn what is the shape of that probability distribution. So, and then once the network is trained, at this time, what you want to do is that you want to marginalize over those probability distributions. And so the way you do that is basically you Monte Carlo over them. So you would put the same input multiple times through the network, and then every time with a different realization of those P distributions, and then collect the outputs that are always going to be different. And that's going to build a distribution over possible values of mu and possible values of sigma. So in practice for us, although so this is what a true Bayesian neural network does, but in practice, it's really hard to train Bayesian neural networks. So what we did is that we used variational inference, where we approximated those P distribution by an approximate distribution Q that is analytic. And then through training, what we did is that we basically learned what are the parameters that describe this analytic distribution. So this made it easier to train a deeper network. So in principle, we can use any distribution we want for the Q distribution, but in practice, if we choose Bernoulli distribution, it actually makes our life a lot easier. So what the Bernoulli distribution is that it's either 0 with some probability P, or it has some value W with probability 1 minus P. So at the so the value of P here is fixed, so it's not the parameter we're trying to learn. The value W is the parameter that we're trying to learn through training. So I'm going to come back in just a little bit on how we fix P, but P is fixed here. And so if you've ever done some machine learning before, you might recognize this as being exactly what dropout does. If you have not done machine learning and you don't know what dropout is, doesn't matter. The only key here is that the reason why it makes your life a lot easier is that because dropout is such a widely implemented method in traditional machine learning libraries like TensorFlow and PyTorch, what it means is that we can basically get our uncertainties almost for free without the need of doing any additional training. So once we have those, we can basically combine the two sources of uncertainties, and this is an example of what we get. So what I'm showing here is the true value of a lensing parameter, the magnification on the x-axis, and on the y-axis, I'm showing the 1 sigma uncertainties for estimated by the neural network for these values. So here, these are all simulated lenses that I'm showing. So we can see that it works pretty well. But then the question is, how do we know if those are accurate uncertainties? How do we know if when I say 1 sigma, I actually mean 1 sigma? So in order to evaluate how accurate our estimates of uncertainties were, we looked at the coverage probabilities of those uncertainties. So what the coverage probability is, for an interval, it's basically the number of times that the true value falls within that interval. So ideally, you'd like the coverage probability and the confidence interval to be equal. So for example, for the 1 sigma confidence interval, you'd like the true value to fall of the time inside the confidence interval. So we calculated those for a bunch of neural networks. So this is what I'm showing here. So here what we did is that every group of 3 bin is a different neural network that we trained with a fixed value of P. So the value of P for all those 5 networks is different, but it's fixed for each network. And then the 3 columns for each network are the 68, 95, and 99% confidence interval. And on the y-axis is their corresponding coverage probabilities. So ideally, you'd like the confidence interval and the coverage probability in the red line to match together so that the uncertainties are well calibrated. So what I'm trying to show here is that basically we can use the dropout rate as a hyperparameter that we can tune to calibrate our uncertainties. So here in our case, in our specific case, we found that with a dropout rate, a keep rate of so a dropout of 3% or keep rate of 97%, we can have well calibrated uncertainties. So just a quick recap on this method for estimating uncertainties with neural networks. We basically, first step is we place dropout before every single weight layer, and then we train with dropout on by minimizing the log likelihood of the distribution we chose for our allotric uncertainty. So in our case, it was a Gaussian, so it's the log likelihood of a Gaussian. And then at test time, we keep dropout on, and we do Monte Carlo dropout. So basically, we input the same test example multiple times through the network, and we collect all the outputs to build the distribution, and then we add the 2 sources of uncertainties, basically the sigma above, and then we get the final uncertainties. So I'm showing an example of this method applied to real data here. So this is a real strong lens. And what I'm showing are 8 different parameters for this lens. So the first 7 are parameters to describe how mass is distributed in the lensing galaxy, and the 8th one is lens magnification. So what I'm showing are the marginalized posteriors for those 8 parameters. In black, the posterior was sampled with an MCMC, and in red, the posterior was just estimated using the neural network. So we can see that in every case, the 2 are consistent with each other, which is great. But then what we see is that the red uncertainties are slightly larger than the black ones. And this is to be understood because for the red uncertainties, we have the uncertainty of the neural network itself that we have to factor in on top. So that's why it's to be expected for them to be a little bit larger. But then the key here is that to get the red lines, it's actually 1 billion times faster than to get the black line. So there's a huge improvement in speed here. And so if we're willing to sacrifice a little bit of precision, but no accuracy, then what we find is that we can get a huge improvement in speed, basically 1 billion times. And the key here is that there's a lot of applications of strong gravitational lensing where getting a precise lens model for the lens is not the bottleneck of the analysis. So having a lens model is good enough for the application that's interesting in that case. So for those kinds of applications, having a method like that can be a huge game changer. Okay, so everything that I've talked about so far was in the case where we're trying to reconstruct the undistorted image. We're trying to reconstruct how mass is distributed in the lensing galaxy. But like I said at the beginning, we're also interested in knowing how does the undistorted image of the background source looks like. So basically, what we wanted to do is know, we want to look at an unobserved image like I'm showing on the left and see if we can reconstruct the undistorted background source like I'm showing on the right. So I'm just going to give a little bit of background first on how this is done traditionally. So if we parameterize the background source by a pixelated image, basically every pixel is a free parameter, then it turns out that going from the source, like on the right, to the lens image, like on the left, is a linear problem. So we can put all the information that comes from the lens in a lensing matrix, and then we multiply the source pixels by that lensing matrix to get the distorted image. So because this is a linear problem, it means that we can invert it analytically. And then the solution is what I've written down at the bottom. So where CN is basically the covariance matrix of the noise in the lens image. So of course, in this case, let's say I have a background source that's 100 by 100 pixels, so not a very big image. In total, I have 10,000 parameters. So this is going to be a hugely under-constrained problem. So in order to regularize it, we need to introduce a prior distribution on the background source pixel. So if I include the prior in my analytic solution, this is where it goes. So that's what ends up being my solution. So I can see how well this does if I apply it to the example I showed at the beginning of this part of the talk. So this is how this linear inversion works, so how well it works on this problem. So we can see that even though the solution is analytic, it's not perfect. There's sort of a lot of noise that leaks from the observed image into the reconstruction. And the reason why it's not very good, it's not perfect, the reconstruction, is because of that prior distribution that we had to put on the background source pixel. So in order to keep the problem tractable, what we had to do is we had to use a very simplistic prior, basically a Gaussian, something we can write analytically. And what a Gaussian prior does is that it basically just constrains the 2-point correlation function of the background source pixels. So this is not a very good representation of the knowledge we have about what the background galaxy should look like. It's just, you know, a 2-point correlation. It's just a 2-point function. So the question we had is, can we do better using machine learning? So with Warren Morningstar, who was my student at Stanford, we looked into using a specific method that's called the recurrent inference machine, or RIM for short. And so what that method does is that it's basically built to solve the equation that I'm showing at the top for x, where in this equation, y is a vector that contains observations, noisy observations. So in our case, it would be the noisy pixels of the lensed image, and x are the parameters of interest. So in our case, it would be the pixels of the undistorted background source. And f is some physical model that goes from x to y. So in our case, it would be the lensing matrix. So it's a linear problem, so f would just be a matrix, and it's the lensing matrix that lenses the background source pixel to produce the lens image. And then n here is a vector of additive noise. So if we know what the noise statistics is, so for example, if it's Gaussian noise, then it's very easy to write the likelihood of y given x, like what I've written in the middle. So it's just Gaussian, because the noise is Gaussian. And then what the RIM does is that it solves the first equation for x recursively by trying to optimize the likelihood. So at every step of the recursion, it looks at where it is in x, so what's its current position in parameter space x, and then it looks at the gradient of the likelihood evaluated there, and then it uses that to output an update to the parameters, the x's. So in practice, it ends up being very similar to what a downhill optimizer does. So just a quick recap on what gradient descent optimizers do. So what a gradient descent is basically a method to optimize any function f recursively. So at every step of the recursion, you look at where you are, and then you calculate the gradient of the function f you want to optimize at that place, and then you multiply that gradient by some constant gamma, and that produces your update. And then you keep on going like that until the process converges. So what the machine learning method, the neural network, does is very, very similar. At every step of the recursion, it inputs the current place in parameter space x, and then the gradient of the function at that place, it passes that to the neural network, and it basically, the neural network uses that to produce the best possible value of the update. So it's basically the neural network tries to produce the best possible value of gamma. But then on top of that, to make its estimation even better, it has a hidden memory state that allows it to keep in memory where it's been in parameter space, and that helps it even better inform where it should be going next in parameter space. So in the case of gradient descent, what we want to do is we want to optimize any function f. In the case of the RIM, what we want to do is optimize the likelihood function. So this is a sort of a schematic way of how the recursion goes. So at every step of recursion, we output our best guess for what the undistorted image of the background source is. So that's an A. Then we use the forward model in B to produce the lens image in C. We pass that to the likelihood in D, and we take its gradient with respect to the parameters X. So these are the pixels of the image in A. And then we pass this in the RM, the neural network in E, to produce the next update. And then the recursion keeps on going like that until it converges. And then during training, what we do is that we show at the end of the, when it's converged, we show it the true answer. We show it where it should have ended up in parameter space. So in this way, the neural network can learn how to properly optimize the likelihood. So once the network is trained, we can test its performances on new data. So this is what I'm showing here. So this is the image that I showed at the beginning of this section of the talk. So at the top left is the is the simulated observed image. At the bottom is the ground truth, and we know what the ground truth is because this is simulated data. On the top the top right, we have the RM reconstruction, and at the bottom, we have the state-of-the-art linear inversion reconstruction method that I showed at just close to the beginning of the section. So clearly we see by eye that the RM manages to really do much better than the best we can do with traditional method, the linear inversion methods. But then to quantify exactly how much better it's doing, we can look at something that's called the coherence spectrum, which is basically the cross correlation between the reconstruction and the ground truth as a function of scale. So this is what I'm showing here. So in blue, it's for the RM, and in red, it's for the linear inversion. And then the key here is that the closer it is to 1, the more similar the reconstruction is to the ground truth. So we can see that on all scales, the RM manages to perform better than the linear inversion method. So this is really interesting because so far we were mostly looking at machine learning methods to increase the speed of our analysis. But in this case, it's sort of the first example that we have in strong lensing where machine learning methods manage to outperform our state-of-the-art analysis methods, traditional analysis methods. So this is really, really interesting. And in this case, the reason why the neural network manages to do so much better than traditional methods is because of this prior distribution that I talked about before. So basically, the linear inversion methods were constrained to using a very simplistic prior in order to keep the problem tractable and analytic. But then the neural network doesn't have that constraint. It's free to learn a very complex prior distribution implicitly from its training data. So what that means is that it can learn a much more accurate prior for what a background galaxy should actually look like implicitly. And so this is what allows it to outperform traditional methods by so much. So a very common critique that we hear about neural networks are the fact that they're not very good once you test them outside of the region where they've been trained in primary space. So basically the question of robustness, how robust they are to extrapolation. So we wanted to test how robust this method was if we extrapolate it, if we look at how it does outside of its training data. So what we did to test that is that we use, instead of using a galaxy as the background source, we use just text. So we're using the text that I'm showing at the bottom left, and then the mock data is at the top left. In the middle, it's a reconstruction from the linear inversion method, so traditional state-of-the-art methods, and then the RM is on the complete right. So we can see that once again, well, first of all, it doesn't break the RM, so that's great. So it means that it's pretty robust against extrapolating to things that are very different from what it's seen during its training. And then the other thing is that we can see that it also, once again, manages to outperform linear inversion methods. So there's not that noise that leaks through the reconstruction. And so it manages to have a resolution that's much better overall, the image, when it's doing the reconstruction. So this is a very good test of robustness of this method. Okay, so let me see how I'm doing on time. All right. So everything that I've talked about so far was when we have, for the case where we have optical data. But in strong lensing, we're also interested in doing analysis of interferometric data. So the thing with interferometric data is that it doesn't just look at the image of the sky, it actually looks at the Fourier transform of the sky. So instead of looking at an image that's like the image that I'm showing on the top left, it actually looks at its Fourier transform, and then it subsamples it at some places, because every pair of antenna that we have in an interferometer is going to measure a single Fourier mode. So depending on how many pairs of antennas we have, we're going to be measuring different Fourier modes in the sky, and it's definitely not going to be all the Fourier modes in the sky because we don't have an infinite number of antennas. So an example of Fourier coverage that we could have is like the black dots that I'm showing on the top right. And so, and then once we look at those Fourier modes that we have measured, we can inverse Fourier transform them back to real space, and then we would get something like what I'm showing at the bottom. So, so the bottom image looks very noisy, but it's not actually noisy. It's part of the signal, and all those side lobes just come from the fact that we have incomplete Fourier sampling. So using a neural network to do the analysis of those data is very difficult. If we were to try to use a neural network to analyze the images directly in Fourier space, it would be very challenging because CNNs are really good at picking up local correlation in images, but then in Fourier space, information that's local in real space becomes very non-local in Fourier space. So it would be very hard for a neural network to learn properly what we wanted to learn. The other thing is that depending on what Fourier modes we're measuring in the sky, so depending on how the antennas are placed, the image that we reconstruct when we inverse Fourier transform is going to be very different. So for example, here, It's the same real image in the sky, so the same sky emission, but then different Fourier configurations lead to very different inverse Fourier transform image, or different dirty images. So if we were to train a neural network to act directly on those dirty images, it would also be really hard, because the neural network would have to learn basically that all those images, those 4 images, are exactly the same thing, which would be really hard for a neural network to learn. So what we thought we could do is to use the RM once again to deconvolve the image and reconstruct basically the true sky emission. So the way that the recursion works in this way is that the RM outputs its best guess for what the deconvolved image of the sky should be. In A, we use the forward model, which is basically Fourier transform and then subsampling of the Fourier modes. In B, to get the Fourier coverage in C that's been measured, that would have been measured. And then in D, we have the likelihood that we form in Fourier space, and we take its derivative with respect to the pixels of the image in A, we pass it back to the RM, and the recursion keeps on going like that. So once we get the deconvolved image, what we can do is we can pass it to the CNN that I talked about before that estimates uncertainties. So this is what we get on real data. So this is actually the same image that I showed before. And this is why this was 1 billion times faster, because this was actually interferometric image and interferometric data, which is much harder to analyze using traditional methods, because the data is just so much bigger. So that's the reason why there was such a much bigger improvement in speed. Okay, so everything that I've talked about so far was in the case where we have a very simple galaxy in the lens. So basically, just one galaxy that can be parameterized analytically by a handful of parameters, like what I'm showing here: position, elasticity, an angle, and so not very complex. But when you look at actual images of strong lenses, like what I'm showing here, things are much more complex in a lot of cases. So here clearly we have 2 main galaxies in the lens, but also if you look at the bottom, there's a bunch of smaller galaxies that clearly have an influence on the shape of the arc. And so this makes using traditional methods for cases like this very, very challenging. So we need to have a parameterization for how mass is distributed in lens in galaxy that's much more flexible. So one thing we can do is that we can use a pixelated image and then project it down to 2 dimensions. And then this would be the parameters that we're trying to reconstruct. So what I'm doing right now for this with my student, Alexander Adam, is that we're using 2 RMs that work in parallel. So the first RM's job is basically the one I just talked about that reconstructs the undistorted image of the background source. So that's the one at the top. And the one at the bottom, his job is to reconstruct that that the pixelated image of the density in the lens and galaxy projected in 2 dimensions. So they work together because they share the same forward model to produce the lens image, and they also share the same likelihood. But then they each take the derivative of the likelihood with respect to their own sets of parameters. So to train a model like this, we need to have a way of generating realistic looking galaxies for our lenses that are much more general than simplistic analytical parametric models. So what we did for that is that we used galaxies from the ILLUSTRISTNG simulation. So I'm showing some examples here. So it's a very realistic hydrodynamic simulation that simulates how mass evolves throughout the history of the universe to form galaxies today. So, but then what we realize is that the ILLUSTRISTNG simulation doesn't have that many galaxies that are massive enough to produce strong lensing. And so with another one of my students, what we've been doing as Lucas Goupil is that we've been training a variational autoencoder to produce more images of galaxies, realistic looking galaxies. So what a variational encoder does is basically a way of generating images from some training data in a way that you produce basically more data that look very similar to the training data that you have. So I don't think I have time to go into the details of how it works. But these are some examples of new galaxies that we can generate this way very quickly using the variational autoencoder. So once we can train the double RM using this method, and this is sort of what we get. So this is extremely preliminary results. So this is in the very, very early stage. We haven't done a lot of work on fine-tuning the network or the training or any such things here. This is just the first test to see if this method will work at all. And it looks very, very promising. So what I'm showing here at the top is the truth, and at the bottom is the reconstruction. On the left, it's the lens image. In the middle is the background source. And on the right is the density, the pixelated density in the lensing galaxy. So it's already very encouraging to see that the neural network manages to pick out from the very little information that it has just through the pixels and the arcs of the lens galaxy, that there is this asymmetry in the lensing galaxy. There's a huge blob in the upper left corner that would be completely impossible to capture using traditional methods. So even this, this quality of reconstruction would be impossible to achieve using traditional methods. So this is a very, very promising avenue for reconstructing more complex density maps in lensing galaxies. So another thing we were interested in knowing is we were wondering, is the neural network doing basically just a dictionary lookup, or is it actually learning something more fundamental about lensing? So we're wondering, you know, when we're doing a training, is it just picking back out the closest example it's seen in its training set, or is it actually understanding some of the physics that we wanted to understand? So what we did to test to answer this question is that we looked at a neural network like the one I just talked about, where we always train it where there has been two galaxies in the lens. So we showed the image that's on the left, and it's trying to reconstruct what's in the middle. And we see that, you know, and many times it manages to do pretty well. But then we wanted to know what would happen if we were to show it without any further training. What would happen if we showed it an example where there were 3 galaxies in the lens? And the thing to understand here is that this is a very nonlinear problem. So going from 2 to 3 images is really, really not simple. So the images configurations to get are extremely different. And we were very surprised to see that in many cases, the neural network actually manages to figure out that there are 3 images in the lens, like what I'm showing here. And so this means that the neural network is not just a dictionary lookup, because during its training, it's never seen an example where there are 3 galaxies in the lens. Rather, it's learning something more fundamental about lensing. It's really learning that correlation of brightness in the lens image relates to overdensities in the lensing galaxy. And this is exactly what lensing is. And so all these tests that we're doing right now are extremely promising for using machine learning methods in places where traditional analysis methods have really struggled a lot in the past. So for example, on the scales of clusters, cluster lensing, strong lensing has been extremely challenging with traditional methods, like the image I'm showing on the left. It's been very, very difficult to do any progress using traditional methods for this problem. Or on a completely different scale, on the scale of galaxies, like what I'm showing on the bottom right, there's a galaxy that I showed at the beginning of the talk that's called the horseshoe lens. And so this lens has been discovered 10 years ago, over 10 years ago, actually. But so far, people have really struggled a lot to produce a good lens model for this lens. And it looks very simple. There's just one galaxy in the lens. There's a single galaxy in the background source, it looks like. And so far, you know, after 10 years of trying very hard, we have not managed to produce a good lens model of this galaxy using lens modeling methods. So there's clearly something weird that's going on with this galaxy. And it would be very interesting to see if we can discover what it is using machine learning methods. Or like I'm showing an image just above that, when there's more than one galaxy in the lens, that's obviously very difficult to do with traditional methods. Or even on a different scale, the subgalactic scales, which are very exciting for understanding more properties of dark matter. The problem of finding subhalos of dark matter in lensing galaxies. This has been a very, very challenging problem to do with traditional methods, but it would be very exciting to see if with machine learning we can help this problem progress further. So I think I'm going to stop here. Thank you very much.
Thanks so much, Prof, for interesting and encouraging talk that talks about how machine learning can assist us in future predictions and analysis. I think it's a very interesting talk. Then we can open questions to participants. I think on the Q&A, I see that there's a questions. There were questions from Kasim Nutondi, but he also indicated that you already responded to some of the questions. I think you can just only take the last comment that he's made on the Q&A part. He says, many thanks for this very thoughtful, provoking talk. I prematurely asked the above questions as I picked up answers from your talk later on. But since we are making distributional assumptions, I would like to get your view on how truthfully training by gradient descent mirrors such assumptions, which are as a rule violated in most real life applications. I think that's a comment or a question that, if possible, Prof, you can respond to. Thank you.
So I think this is a very, very interesting question. So there's many ways to answer this question. So I think the most important assumption we make that's the most likely to bias our results is about the distribution of the training data. Because like I mentioned when I was talking about the source reconstruction, it's really the training data that puts an implicit prior on the data we're expecting to see when we actually apply this on real data. So obviously in our case, because we are using simulated data, it's always a big challenge to know if our training data is a good enough representation of what the actual data that we're going to see is. So there has been a lot of, there's been a very interesting paper on this specific subject applied to the case of strong lensing. I think it came out last month. It was a paper about, I forget the last name of the first author, but it was Sebastian something, and Phil Marshall and Risa Wexler were on the senior people on the paper. So in that paper, what they did is that they looked at how you're putting basically an interim prior on your neural network through your training data, but how you can use hierarchical Bayesian modeling in order to correct for that interim prior if your actual test data comes from a distribution that is very different from your actual training data. So they look at different cases where the distribution of test data that you have is actually much narrower than the distribution of training data that you had, which is usually the regime you would be in machine learning. Or what if it was sort of skewed towards one end of your training data, or if it had completely different correlations between your different parameters, and how you could correct that bias that you would otherwise introduce using that you would otherwise introduce if you just used regular methods. So yeah, what they used was Bayesian hierarchical modeling to do that.
Thanks, Prof. I think you did respond broadly to that question. I hope you've answered the question that was raised. When I look at the charts, I think there's a question from Quinn Reynolds. Thank you for fascinating presentation, Prof. Amazing work. Do you plan to continuously update these models as experimental data from the new observation starts coming in by incorporating it into the training and test sets alongside your simulated data? That's the question, Prof.
Yeah, absolutely. So this is a very, very important point. So when we were when we were doing the neural network that was going to be tested on Hubble data, we specifically tuned the training set so that it would be a good representation of what Hubble data should look like. So we had the same, so our training set had the noise statistics that was similar. It had a range, so we didn't have a single noise statistics, but it had a range of noise statistics that were so would encompass basically what the Hubble noise would be. All the observational effects were tuned to be very similar to what you would see in Hubble data in terms of hot pixels, faint cosmic rays, and different kinds of mass that you would need because you have a lot of different effects in Hubble data. And so it's definitely very important to when you're just it's similar to the question that was asked before about distribution of training data. So it's very important to have your neural network. So to have your training data, that's a good representation of the actual data that you're going to be testing on. So for example, when we're thinking about doing the analysis of LSST data, the resolution is going to be very different from the resolution that we get with HST, just because LSST is a survey telescope, and so the resolution is going to be much lower than the high quality data you would get with HST. And so because of that, we'd have to build test data that is going to be lower resolution, and it's going to allow different kinds of constraints like that. So it's definitely when we're preparing pipelines for those observatories, it's very important to have good simulation pipelines to basically allow us to produce simulated data that will look a lot like what we think is going to be coming out of those observatories. But also once we start taking data, actual data with those observatories, then we can go and test all of those assumptions and see if the simulated data that we produced was actually well represented, or if the actual observatory is very different. And in most cases, obviously, there's a lot of corrections that need to be made. So of course, it needs to be updated, and it needs to be updated depending on what specific application we want to do too with machine learning.
Okay, thanks again, Prof. I think the response from the participant, they are also thankful of your talk. it's unfortunate that during this situation we are living in, we cannot have further engagement, as we'd love to have such a live engagement with you. And we hope maybe in future, we'll plan that you can visit South Africa and we can organize something. I think the participants are also supporting for the talk that you've just presented. And as indicated, it's also aligned directly to the theme of our conference of this year. With such words, I think there's maybe we can take the last question. Okay, there's a last question here that I think you can take. It's from Happy Sitola. He says, will this be able to be used on radio astronomy such as SKA, Square Kilometer Array? Are you part of the team? That's the question.
So yeah, that's definitely so. So the RIM that I was talking about for reconstructing deconvolved images of the sky is definitely one of the applications that we have in mind to apply to SKA. So I know it's probably very relevant to what scientists are thinking about in South Africa. I am not part of the team, but I have been very interested in getting involved more with 21 centimeter observatories and data. So I have been actually developing methods in general for different parts of challenges that we are going to be facing with 21 centimeter data analysis, in particular, producing simulations of 21 centimeter data, because it's very challenging right now. We have to rely on hydrodynamical simulations, which are very expensive to produce, or HOD models, which are sort of an analytic way of in-painting neutral hydrogen into dark matter only simulations. And those can have a lot of different biases. So I've been looking into machine learning ways of producing more 21 centimeter data in order to facilitate the analysis of actual data. And another thing that I've been interested in is using machine learning methods to help with the problem of foreground subtraction when it comes to 21 centimeter data, because as you might know, it's an extremely challenging measurement to make, because the foreground that comes from our galaxy and also down on the Earth are about 5 orders of magnitude larger than the signal this cosmological signal that we're looking for. And so extracting the signal, that is 5 orders of magnitude below the foreground is very, very difficult. And we've been looking into machine learning ways that we can tackle this challenge. But the problem of specifically deconvolving images like the images that you will get with SKA, it's something that I'm definitely very interested in. And we were planning on probably get a student to be looking into this problem of using the RM for specifically this application, yes.
Thanks, Prof. I think this was the last question. And I think I'm not sure we'll able, because we are running out of time. We've got only 6 minutes left. Let me see. I think just a response from Happy saying, thank you for the response to his question about the SKA involvement. So with that word, Prof, let me thank you for your participation in this session. And also let me thank all the participants for this session. And again, let me also make one important announcement for participants to say, we will be having the last session of the day, which starts at 17:45. This is a very interesting session, entertaining and fun session, which is the vendor Crossfire. I encourage all of you participants to join that session that starts at 17:45. And the chair for that session will be Dr. Happy Sitola. All our sponsors, which are our partners for this conference, who make sure that our conference becomes a success, will be participating at that session. So I encourage all of you to make time to attend that session. Our sponsors from Intel, Huawei, Dell, AMD, NVIDIA, and Altair will be participating in that session. So I greatly want to encourage all of the participants to participate in that session that starts at 17:45. And again, let me thank you for your patience and for being part of this session. Thank you very much and keep well. Thanks.
Thank you very much.
Good afternoon, ladies and gentlemen. We are going to commence the vendor Crossfire session shortly. Our first speaker will be a pre-recorded clip that we will play out, and from there we will continue with the vendor Crossfire.
Hi everyone, I'm Addison. Hi everyone, I'm Addison Snell with Intersect 360 Research, and I'm thrilled to be joining the CHPC National Conference again, and I'm especially grateful to Werner and happy for inviting me to participate again, although I'm quite sorry that I'm not able to attend in person this year. I'm coming to you from the other side of the globe in Mountain View, California, and I'm really hoping that I'll be able to get back with all of you in person in 2021. I'm going to give a very short post-SC20 market update talk today to give a very quick overview of some of our research and highlights from what we thought were the top trends at SC20. There's a longer version of our pre-SC20 market update talk available on our website, and I'll show the URL for that at the end of this talk, and then we'll get to my very favorite part, which is Vendor Showdown. I'll be joined by Dan Olds, as well as a student volunteer from the student cluster teams, and we'll take on the vendors who are sponsoring the event, get to hear what they have to tell us. So a very quick overview about the HPC market this year. Now we're still showing 2019 numbers because 2020 is still in progress as a forecast year, but we're talking about a $39 billion market. That was up 8.2% year over year from $36.1 billion in 2018, about a point higher than we had forecast, with government taking over from industry in terms of leading the way in growth rate. And that's a trend we expect will continue over the course of the upcoming years in the forecast. But here's what was very interesting. The major on-premise portions that we would normally think about, the servers, the storage, were really only between 2 and 3% growth year over year. So how can you have those big portions of the budget only grow 2 to 3%, and then you have 8.2% growth in the industry? And the answer, of course, was cloud is a big part of what we were looking at, but it wasn't just strictly cloud as it gets reported to us as cloud. When we looked at the numbers a little more closely, we could see that cloud was having an even bigger impact with what we could call cloud-like types of environments that go into other as-a-service types of deployments. And I'll explain what I mean about that here shortly. This is a graphical depiction of the year-over-year change, 2018 to 2019. You can see the major portions there at the bottom, the servers and the storage. Were really relatively low growth rate compared to everything else. And the cloud, the second from the top, you can see visually it is a big growth rate there year over year in that orange, but it's coming from a relatively slow pace. The question then it becomes, is that the full influence of cloud? Here we're showing the actual numbers behind that data. We've let this out publicly now. Normally our clients get this level of detail. And I've got an orange arrow there on the 17.8% growth year over year for cloud computing in HPC to reach $1.4 billion. That's $217 million of growth year over year. Is that the total effect of cloud in the market? Actually, it's not. There's more than $1.4 billion if we really get under the covers and look at it. Well, if it's not on the cloud line, where is it? And the next thing to do is look at some of these other high growth numbers. Software, which is the second biggest portion of the budget after servers, bigger than storage, had $700 million of growth, just about at 8.2%, well over the growth rate of the servers and the storage, and then very high growth rates in services and in other. Now, we don't normally like to have other as a major category. And in fact, when we looked at the growth in services and software, it fell down to other subcategories of other: services, other; software, other; and then this big other category. And when that happens, we like to take a look at the descriptions of what people told us they were doing to see, as analysts, should we recategorize that somewhere? Where does it really belong? And this is the beginning of an interesting trend. When we look at software, what we found was this other category that's always there that suddenly had a big spike to 3.5% of the software category. There's about $300 million worth of growth there. And what it was really describing was software as a service types of contracts that were appearing on the software line. Imagine you have a contract with some software provider with utility pricing built in, and then they're passing through to cloud or utility computing on the back end. That's a way that cloud computing can hide on the software line. Similarly, with services, we had a big jump in services from under 3% of the budget in 2018 to over 8% of the services budget in 2019. That's over $200 million in growth in services other. This is primarily things like cloud managed services contracts. Imagine that you're contracting with a company like R Systems or Rescale or Nimbix, and they're doing HPC managed services and then including cloud or utility pricing in that. That's a way that now cloud can show up on the services line. And then other at the top level was also hiding these managed services, facilities outsourcing kinds of contracts. So when we look at directly measured HPC cloud spending that people tell us directly is in their budget, yeah, that was $1.4 billion. But now we're looking at an additional 200 to 400 million of SaaS-like things on the software line, 200 to 400 million of managed services types of contracts that are related to cloud in the services budget, other cloud types of contracts or outsourcing types of contracts in other budgets. It adds up to about $2.5 billion, give or take, or $1 billion more than we had been counting. And that still excludes things that some of the cloud providers might like to count with regard to cloud native machine learning. That's not part of an end user's HPC budget, but the cloud provider in of itself, a Google, Facebook, Microsoft, whoever it is, AWS, is doing machine learning with their own infrastructure. That you could call HPC if you want. It's not part of anyone's HPC budget, so that's not even showing here. That would elevate you to well over $3 billion if you included that. It's important for me to state we're not adding $1 billion to our forecast here. This was already accounted for in budgets that we were already tracking. It's just getting a little more granular on where this comes from. And what it indicates to us as analysts is this is a new trend. And when we do our new round of budget surveys in early 2021, we will update that methodology to better account for more types of cloud-related spending. I also want to quickly check in on the forecast, because the major thing going on this year is we're dealing with the effects of COVID-19. Now, these are mostly near-term effects. They're dealing with the current year, 2020, next year, 2021. We think there will be an echo effect into 2022, 2023, and by 2024, we're mostly back on the line of where we would have been otherwise, looking at 7.1 compound annual growth rate from 2019 as a base up to 55 billion in 2024, and with government continuing to grow in terms of the major sector, and cloud continuing at over 20% compound annual growth rate. But we really want to look at, in the near term, what do we think is the effect of COVID-19 on this market? And the good news is we've seen this before. This is in general what happens in HPC in the time of a recession. And what you're looking at here is a generalized picture with no years on it. You start in year 0 before there's a recession, and then you have a 5-year forecast, years 1, 2, 3, 4, 5, with a smooth growth rate, let's say for the sake of argument. Then a recession happens in year 1. This is the basic picture of what happens. In year 1, you have a dip, but mostly that's not sales that are canceled or acquisitions that are canceled. Mostly what happens is things get delayed. The sales cycles stretch out. It takes longer to get things approved. And there's a certain number of acquisitions that get deferred, which means some of them fall from that year 1 out into year 2. So the revenue is delayed, not canceled. What happens then in year 2, as a normal economic activity resumes, the sales cycles pull back in, and then you get a year that has essentially extra months in it because you get all of the sales you would have had in year 2, plus sales that had been deferred from year 1. So you get a bump above the previous forecast. And what you've really done is push some of the year 1 sales into year 2. And what that looks like is you get this artificially high growth rate that looks phenomenal from year 1 into year 2 that's marked there. And that's really an artificial effect. And then you can have an echo effect in years 3 and 4 that are mostly due to budget cycles where people don't make major purchases in back-to-back years, and then it tends to level out by year 5 again. Now, there is some revenue that's lost and not deferred. The troughs in years 1 and 3 are deeper than those peaks are high in years 2 and 4, which is to say there is some lost revenue. It's just, it's incremental. Most of it is deferred. And a big part of what we've modeled is how much do we think is deferred by industry and how much do we think is canceled by industry. And the good news is we've seen this before. Good news for certain definitions of good. This is what the market looked like in the years following the recession in 2009, starting at a 2008 baseline with a smooth growth rate there in orange. We saw the dip in 2009, the spike in 2010, a little bit of a wiggle in 11 and 12 before coming back and hitting the line in 2013. This is not an exact replica of what you just saw, but it is, I think, really indicative of the pattern that we expect to see with a near-term recession. So for the COVID-19 adjustment on our forecast, we're looking at a 10% below baseline forecast this year for 2020. That's $4.2 billion below what we had previously forecast, which doesn't mean it's a 10% fall year over year. We had been forecasting growth. We're forecasting 3.7% decline year over year, which would be the first year of decline since 2009. We come back with an echo bump year in 2021, and then the reduced effect in 2022 and 2023. The significant forecast risk here is how much of this revenue, or rather, how long does COVID-19 last as an economic damper? And do we really get back to more or less normal economic activity in 2021? We're watching the manufacturing and energy spaces very closely to see to what extent those might extend farther in 2021. This is that vertical market picture: energy, retail, large product manufacturing, the hardest hit vertical markets. Conversely, biosciences and some of the national research actually is stable or even goes the other way, as we've seen a lot of biosciences resources with HPC deployed to fighting COVID-19. The only thing I want to say about products and services is that cloud actually follows the opposite pattern, because if you constrain the on-premise deployments of servers and storage, then you get an actual acceleration of cloud in that year, because people will go a certain amount to cloud in order to compensate for the reduction in on-premise resources for that year. And regions, when we first gave the guidance back in March that this was coming, we would have thought then that Asia Pacific would have been the hardest hit region, and US, Canada maybe the least. By the time we actually came out with this in July, it looks like US is the hardest hit area economically, followed by EMEA, and then Asia Pacific and China have been on more or less normal economic activity. And that's really what we're forecasting, is not the virus itself, but the economic effects of the virus. How is this looking? Right now, straw poll looks like 2020 is trending according to this. We won't update this again until early 2021, and then we'll take a look at what did 2020 do, and do we need any ongoing effects to the forecast in 2021. Going into stories from SC20, the biggest thing is the celebration of Fugaku, which of course started at ISC in the summer, but that has been upgraded, not only reaffirmed, but upgraded for its position as world #1 at RECON. Just such a phenomenal achievement, and to have deployed it ahead of schedule such that those resources could be brought to bear in the global fight against COVID-19 is a great achievement for RECON, also for Fujitsu with the tofu interconnect, and most importantly for their A64FX ARM processor, really establishing ARM as a viable processor, not just for HPC in general, but for the pinnacle of supercomputing. Big applause to Riken for this achievement, and to Fujitsu for Fugaku. I mentioned that ARM chip because it's related to the top trend that we're watching here. Also related to that top trend, we keep watching the effect of AI on HPC budgets. What we find is when AI capabilities are built into an HPC budget, we see a big effect on that budget where the growth expected is higher than in areas where AI is not present as part of the HPC budget. And that's part of the secondary effect of AI on the market that we've been modeling as part of our research. It affects not only the budgets, but of course the configurations. We've seen a lot of GPU deployments related to machine learning. And that's really where the major trend has been right now that we were watching at SC20 with processor consolidation. Now there's corporate consolidation as part of this. NVIDIA is acquiring ARM, AMD is acquiring Xilinx, Marvell is acquiring Inphi. But the bigger thing is the technology consolidation, where we're going to have both CPUs and GPUs from Intel. We're going to have both CPUs and GPUs from AMD. Presumably, we're going to have both CPUs and GPUs from NVIDIA, or at least the NVIDIA ecosystem, depending on how they play their ARM acquisition. And we actually did a big there are product announcements around this SC20. These, I think, were the most important product announcements. The AMD MI100 GPU, I'm going to list first because they were keeping HPC square, traditional HPC square in the crosshairs of this, whereas NVIDIA's messaging has been very AI and machine learning heavy. AMD is going square at 64-bit computing here, advertising over 10 peak teraflops, actually 11.5 peak teraflops of 64-bit multiply add. And of course, they have benchmarks for 32-bit, 16-bit mixed precision and below. The other thing they talk about is their CDNA versus RDNA architecture. That's compute DNA versus Radeon DNA for the computation versus the graphics. NVIDIA, of course, had a lot of announcements, most notably the 80 gigabyte variant of the A100 going onto the HGX baseboards. That's not as a separate PCIe card, but goes into products like the DGX A100, now available at 640 gigabytes. And interestingly, the DGX Station A100, that's a workstation or desk side. Interesting, I'm a huge fan of workstation in general for HPC. Interesting to see it in a machine learning focused deployment like a DGX. I'm going to be curious to see how that plays out. But the biggest HPC news from NVIDIA is actually on the Mellanox side with the NDR 400 gigabit InfiniBand adapters across the full range of, actually not just adapters, switches, cables, and those data processing unit DPUs. Important because it keeps NVIDIA keeping up with that drumbeat of performance with Mellanox going forward with new generations of deployments. And Intel had key announcements also, most notably the early access of XE-HP GPUs in preparation of the delayed Ponte Vecchio GPUs that are going into Aurora, the XE-HPC, to get the development going on those. I think that's very important since the other GPUs are already out in the market. They also teased out additional details of their upcoming Ice Lake CPU and One API Gold. They're competing developing environments here, ROCm from AMD, CUDA from NVIDIA, and then One API from Intel. I think a lot of this war really gets played out in software. We've been doing research around end user ratings of all the different vendors in this space. And for this presentation, we actually have released some of the data around processors in particular. All the full data on this is all with our clients, but looking at processors, of course, you would expect Intel and NVIDIA are dominating what most people have been using. NVIDIA actually shows up very well here, and Xeon is nearly ubiquitous. And then everything else, AMD, and then everything else is much farther back. But when you look at technical impressions, AMD's EPIC starts moving up the list. NVIDIA is on top here. And if you weight it according to how much experience people have, well, all the scores go up. People are more impressed with the things that they buy. But EPIC actually nudges ahead of Intel Xeon in the technical weighted section of this, the technical scores weighted by how much experience people have. Future prospects for HPC, when you start looking ahead, again, all the AMD things start coming up, particularly GPUs from AMD are the thing that take the biggest leap in the surveys and might get a drag along as these things start to consolidate all from one vendor or another. The biggest point from this selected conclusions is that the relationship between the CPU and GPU is going to define the next chapter of competition here. And what the market is saying they want is Intel CPUs or AMD CPUs together with the NVIDIA GPUs. But that's not the way the market's developing. And eventually, I think people are going to start to feel the need or pressure to choose an all Intel, all AMD, all NVIDIA kind of environment. And then it's going to be very interesting to see how this starts to progress. We have all these different categories across all of these different vendors in the different categories. AWS does very well on the cloud side, although really just looking at the number one belies the notion that it was AWS, Azure, and Google really in the top three, and then a far drop down to everything else. There is a longer version of most of the information in this presentation on our website from our pre-SC20 market update webinar at intersect360.com/presentations. There are all kinds of ways on this to get more information from Intersect 360 Research, including finding our podcast This Week in HPC. And now I really look forward to getting to Vendor Showdown, being joined by Dan Olds and one of the students. We're going to bring the vendors out and get to talk to them about some of their solutions. Thanks very much. Looking forward to Vendor Showdown.
Hi, everybody. This is Addison Snell back with you again. And as I said in my pre-recorded presentation, we're very excited to start Vendor Showdown. In this format, each of the sponsor vendors has 5 minutes to present up to 3 slides. And then Dan Olds and Siobhan Chinia from the Student Cluster Competition is a representative from WITS. They've been hard at work doing the student cluster. The 3 of us will form a panel where we're going to spend an additional 5 minutes to ask a set of questions to the vendors. We've been meeting this morning and going through the slides, and we're going to watch the live presentations themselves. And we'll try to ask some interesting questions of the vendors based on their presentations. At the conclusion of each of those, there will be a poll question where you as the audience will be asked to rate how did the presenter do, both in terms of their overview of their technologies or solutions and answering our questions. Just do a single question, scale of 1 to 5. 5 is the best, 1 is the worst. Just tell me how you think they did. And then at the end of the entire Vendor Showdown, we'll reveal a winner, so to speak, who had the best overall score from the audience. So please do pay attention. These are going to be rapid fire, fast pace, and we really appreciate the sponsors stepping up to this lively format to keep all the vendor talks really engaging and entertaining.
I gotta tell you,
Dan.
Addison, the tension is so thick here you can cut it with a knife, as it always is before the Crossfire session. I know that I have
that's because you're one of the panelists, Dan, and they never know what you're going to ask.
I do have some extra angry questions, or at least I'm working on them as we speak right now. And really want to welcome.
What I really want to hear is Siobhan's take on it.
Yeah, and that's what I wanted to welcome Siobhan. He is with the WITS team and the Student Cluster Competition. And as we've done for the last few years, we brought a Student Cluster competitor in to give us a different perspective and oftentimes ask those sort of innocent questions that turn out to be a little sticky.
Siobhan, would you like to say hi before we start?
Yeah, hi everyone. Looking forward to this.
I interrupted you, Dan. Go ahead.
Oh, I was just going to say that sometimes those simple questions really cut to the heart of a matter. Like,
absolutely,
what does this really do for a customer? That sort of thing.
All right, well, let's dig into it. First up is Kirti Devi from Intel.
You have
Hey, good
5
morning.
minutes, Kirti.
All right, let's get started. Morning, everyone. I'm Kirti Devi. I'm Director of HPC at Intel. Most importantly, Judy, can I have my slides, please? Oh, all right. I still don't see my slides, hopefully.
Apology, Kitty, just 1 second. We're just loading them for you.
All right, no
Kirti,
worries.
your time will not start until that slide hits the screen.
Excellent.
just-
That 30
just a
seconds
point
are
of-
important.
Yes, I know. Oftentimes these races come down to the last seconds and that last point that you get in that sways the audience in your favor.
Truly.
And we'll
So-
just go through the preliminary
Why-
slides here. There's a couple of them. Your slides have been put into a larger deck, Kirti.
Okay, we can start with my first slide, Rudy. That would be great. All right, so thank you. Next slide, please. At this moment, as Addison talked about the COVID, I wanted to just acknowledge our frontline workers globally who are helping protect all of us in these unprecedented times. In these times, I think technology in HPC is becoming more critical than ever. And just as more information sharing, Intel created the Pandemic Task Force Response Initiative in April, and we have deployed about $50 million towards helping save lives, helping find the cure, and deploying HPC infrastructure in this space. At this point, I also want to acknowledge our partners who are using Intel technologies to help us solve the COVID-19 challenges, both from a drug discovery, pandemic response, and various advanced treatment options. Next slide, please. So one of the focus areas of my discussion today and my proposal is Intel has been in the HPC business and segment for decades. And we do this by continuing to innovate and in partnership with the industry. As we look at the focus areas for us, it's both hardware, software, making sure we have standards and also making sure we try to do this with our ecosystem of partners. And this is just an acceleration across these areas and trying to get to exascale and beyond exascale. So just as an example of our innovation with the industry around the software space, Intel is the #1 contributor to the Linux kernel and maintainer to the Linux kernel, #2 in the maintainers to the Linux kernel. We have been responsible in partnership with the industry for driving the SSC1, SSC2, the SIMD extensions. In addition, our math compilers, math libraries and the compilers have been deployed by our customers and partners across the board. From a standards perspective, Intel has been a founding member and continues to be participating in driving standards which help deploy high performance computing across the board. This also drives innovation as it's easier for customers to deploy solutions that are more standardized. And in the third segment, we continue to work with our ecosystem of partners to ensure that the software applications take advantage of the built-in hardware performance architecture instructions. This, in our mind, this innovation across these areas drives exascale and will continue to drive technologies beyond that. For instance, when I think of this, our investments in both in quantum computing and neuromorphic computing, working in conjunction with the industry is something that we have to look forward to in the coming era of HPC. Next slide, please. And most importantly, as we talk about our investments in high performance computing, Intel is deploying a broad base of solutions and products and investing in high performance computing. So let's start with, on the left, advanced architectures. Intel has a range of products and solutions for various workloads. Addison talked about the evolution of high performance computing with cloud computing, with artificial intelligence, adding to the HPC workloads. As we look at our product portfolio, you can see we have Xeon. We have announced the XE GPU architecture, which is being deployed at Argonne. We also have Habana's portfolio, the Movidius portfolio, the FPGAs. And all of these help us drive high performance computing and innovation and meet the customer demands. Frankly, if you look at this segment, customers are doing bleeding edge technologies, and this will help us drive there. On the second bucket, we have software solutions. Our One API initiative is truly out of the mindset of software first. It simplifies programming and optimizes performance across diverse architecture. We have always published the Parallel Studio XC toolset, which helps drive tools in this area. We have memory technologies, we have interconnects that we are investing in. Most importantly, from a manufacturing perspective, given our history, we are continuing to innovate in manufacturing with a new packaging technology called Foveros. And the last pillar of our innovation and investment is around silicon-enabled security at all levels. So if you think of security being important, everything from the client, the edge, the data center, we include security at all levels with our products. Most important message as I wrap up this talk I'd like to deep behind is there's several innovations that Intel is driving and investing in this segment. And we have been in this segment for a long time, and we are committed to being here with you, in partnership with you. Thank you for this opportunity.
Thank you, Kirti. That was very nicely done. Now time for the questions. Go to Addison Snell first. Addison, throw something at her.
Thanks, Kirti. I really appreciate the questions. I like the forward-looking nature of this as well. I'm going to start by going all the way out into the future. How does Intel's experience or leadership with traditional microprocessors translate into some kind of advantage with quantum computing?
Absolutely. Addison, it's a great question. We look at quantum computing as the next generation in computing. And not only us, I think the US government had recognized the potential of quantum computing. Intel is one of the 5, is part of the QNext project, which the White House Department of Science and Technology is funding with Department of Energy and Argonne. And the way we look at quantum computing is we need to invest today in technologies that will drive future computing. So we are providing the entire stack of quantum hardware, software, algorithms in conjunction with the industry to the QNext pack or the QNext initiative to help drive computing to the next level.
Very nicely done. Siobhan, what do you think?
I'm interested to find out what does Intel do to ensure that developers and researchers are effectively using the Intel products? What are the few things?
Absolutely, Siobhan. We work with several universities and academic research institutes. So if you think of our products and technologies, we have, both from a software and hardware perspective, various initiatives. If you look at the software side, we provide the software tool set, the compilers, the libraries, and the performance analyzers for free for download to the academic institutions and organizations. This is part of our strategy to make sure as new engineers and researchers evaluate Intel technology, it makes it easy for them to use it. And of course, we are hoping more and more people join the high performance computing research and academic programs.
Okay, great. Now it's time to get mean, a little bit at least. So Intel has taken several runs at building accelerators. We had Larrabee, son of Larrabee, son of Larrabee. And maybe a few more past that. It seems like you might have struck a pretty good combination with your new GPU, but I'd like to get a little more information on it and how you feel it stacks up against the competition.
Absolutely. Great question, Dan. We have,
Good at that.
and I'm excited to answer it, to be honest. So with the XC product line that was recently announced, in fact, a year ago now, which is the Ponte Vecchio product for high performance computing, we look at this product as a grounds up product, totally focused on the HPC market, right? We are not burdened with the other products in the market have in terms of graphics, heritage, or any other segment focus. So we look at this as an investment. And from a timing perspective, if you look at AI, if you look at the things that people are trying to work on and the workloads that are evolving, we think the product timing is perfect, right? We are planning on using several of our new technologies that I just barely managed to touch on in my presentation in terms of our processor packaging technology called Fervoros, which will be part of this new architecture and will be used in the XC product line. We are planning also using our Sapphire Rapids, which is our next generation processor technology for this solution, which the XE platform, the XE accelerator will run on. In addition, most importantly, I think from a timing perspective, given the heterogeneous nature of computing, the One API initiative that we have launched, where we will have software that will enable developers, engineers to work across various architectures, I think it's critical. So we look at this truly as a differentiator and a competitive advantage as we enter this market with a strong portfolio and a strong technology to support this product line.
Okay.
I'd like to ask
Did I
a quick
answer your question, Dan?
It does. It does. Addison, for the follow-up.
I'd like to ask a quick follow-up on One API, particularly as it relates to competing development environments for, say, CUDA or ROCm. AMD is advertising tools to help migrate from CUDA into ROCm. Can you put One API into context with other development environments out there that people might already have experience with on the accelerator side?
Right, absolutely. Our goal with One API, Addison and team, is to ensure that the programmers have to only develop one and they can deploy the solution around with heterogeneous environments, right? So if you take a look at CUDA, we have an opportunity for NVIDIA to utilize One API. It's a completely open spec. We have, in fact, Codeplay, one of our partners who's working on a CUDA extension for One API and utilizing it. And I think similar efforts are underway with the AMD software tool set as well. So we look at this as an opportunity to almost equalize the playing field, right? Make it easier for programmers without having to develop separate libraries, separate compiles for various architectures. So we are pretty excited. We've had positive response from the ecosystem and our software partners around it. So as we mature into this spec, as we get more and more software partners writing to it, I'm sure we'll see some of these other competitive architectures also utilizing One API.
Have you received a call yet from NVIDIA or AMD saying they want in?
Honestly, Dan, I am not the point on One API, but hey, we have NVIDIA and AMD on the call today. I will leave my email. Please feel free to reach out.
Well, maybe we'll ask them. Maybe we'll ask them. Well,
absolutely. I am not aware, to be honest. I know there's concerted efforts at Intel around this space.
Thank you very much, Kirti.
Thank you so much.
Absolutely a pleasure, Addison and Dan and Shivan.
Yes. So if you would like to, if we can get the slides back up.
We've got a poll question for the audience now.
Yes. So
there it is.
Please rate how well you think Intel did at presenting and answering our questions. 1 to 5 scale, 5 being excellent, 1 being well under excellent. So who do we have up next?
Next up, we're going to have Del. That's going to be Adnan Khalil as the presenter, and we're looking forward to his presentation.
Yes, we are. So please, everybody vote now.
Okay, we
One
can still
vote
see the
each.
votes. We can still see the votes coming in. If we can give it 20 more seconds, perhaps.
We can do 20 seconds. So Siobhan, what'd you think of Intel?
I think it was well answered. I think we tried to throw difficult questions at Kurti, but I think she handled it well.
She did. She did.
Yes.
Nothing through Kurti.
Yeah.
And she's hometown. She's from where I am, up in the Northwest.
Beautiful area, Dan.
It is. It is.
All right, that poll is now closed. Thank you very much, Kirti, for your presentation. And now Adnan Khalil from Dell.
My pleasure.
Hey, good afternoon. Good morning, everyone.
Good morning.
Hey, it's good to see some familiar faces.
You're on.
All right, so
Let's get your slides up.
Okay.
And that is your logo.
That's a very old logo, but yes, it is.
Is it?
Yeah.
I went to the website and it looked current. Okay.
You know, we change it often enough that, you know, we want to confuse people. But...
It works. It works. Okay. So let's get your first slide up. Next slide, please. And go.
All right. Thank you very much for the opportunity to talk to all of you. Hope you're all having a great conference so far. My name is Adnan Khalil. I'm part of the global HPC team here at Dell. I've been with the company for about 5 years, and I will be telling you more about why and how Dell really differentiates itself as compared to its competitors. So the next slide, please. So, you know, as a company, we've been through we've been doing HPC for over 2 decades. In fact, you know, the very first HPC cluster was built in Cornell University. That's been documented back in 1999 in the Department of Mathematics. Now, I say documented, but you know, even before that, you know, people were building Beowulf clusters using Dell components, you know, well before that. But you know, we've gone through several iterations of renewing our strategy, and in the latest version of our strategy, it's ultimately based on this philosophy, this of 3 pillars that we've looked at, and this has been fairly consistent over the past like several years, I can say. The first one is about advancing HPC. The next one is about democratizing HPC, and the last one is about optimizing HPC. And I'm going to talk about each one of these just to give you some more context. Now, you know, although Dell has a very strong showing in the top 500, in fact, we have the rare distinction of having the fastest academic supercomputer, which is ranked in at number 9 at Frontera Attack, and also the fastest industrial supercomputer, which is HPC 5, ranked in at number 8. In Italy by ENI. It's really not about the top 500. It's more about the top, you know, 5,000 and beyond, and which leads me into our next pillar, which is about democratizing, because you know the work that we do in the high end bleeds into making the systems more usable, making them easier, and in terms of the economics as well. So it's really about making it more accessible. And even when you talk to Michael Dell, you know, this is something that's really close to his heart, that he wants to make sure that, you know, it's not just the top institutions that have access to the latest technology, but it's also everybody else. Because ultimately, a lot of really good science happens outside of the top 500. And ultimately, if these systems aren't really easy to use, you can't really support them, and they aren't based on open standards, then you're not making it easier for the customer. And that's something that, you know, we've really taken to heart. All of our platforms designs are based on open systems. We don't believe in sort of tying you to a single vendor. A lot of the times, you know, we have interfaces that work very nicely with other vendors as well. So, and that, is the last tier, which is the optimizing of these systems. So the next slide, please. Which leads me to the next point, which again, as even though Dell is a very large company, you have a lot of resources at hand. The HPC group, for those of you who know us, is actually quite small, and it's really based on just like several handful of individuals that are really dedicated, passionate about working with customers and solving their problems. And this is no better illustrated than at the HPC and AI Innovation Lab here in Austin, Texas, where not only do we have a number of benchmarking systems, this is also the place where we have all the latest technologies. In fact, a lot of the early silicon from our great partners like Intel, NVIDIA, AMD is available here, and it's available to our customers as well. We don't charge for our customers to access this, and it's a great place for you to test your early designs. In fact, a lot of our product development even happens at the Innovation Lab. And we have three large benchmarking systems there. The first one is Zenith, which was until last year part of the top 500. So that's no small feat. And we hope to get it back as part of the top 500 soon. But again, that's a very large system for a petaflop in computing capacity. But we also have a number of different storage systems. So if you're looking at a balanced architecture with different types of high-speed interconnects or InfiniBand and Omnipath, or even Ethernet, this is the place where you can try out those architectures. And we've got our experts on hand to help you to make, to really make it easier for you to sort of benchmark and do the comparison and understand the results. The next slide, please. And really what I want to leave with is that, even though Dell produces the platforms, it really is the spirit of collaboration at the end of the day. That we work with some of our wonderful technology partners, which, without which innovation could not be had. But it's really, working with all of these academic centers around the world where, we have managed to produce solutions that meet the needs of our customers. In fact, again, I mentioned about Frontier, which is ranked number 9 as part of the Texas Advanced Computing Center. That's one of our premier institutions that we collaborate with. We've got the San Diego Supercomputing Center as well. Now, again, we've got these centers of excellence spread across the globe. We've got several in Europe, one in Asia, one in Australia, and not to mention, we've got one right there in the CHPC Center in South Africa. And again, we're really proud about these centers because a lot of the innovation that we do comes out of these centers. For example, Cambridge University is responsible for developing some of the latest storage technologies with parallel file systems and flash systems and so on. And the University of Pisa has been one of the leading institutions when it comes to
Adnan, you're at 6:36.
Okay, all right. Well, let me wrap up then. So University of Pisa is one of the places where they have developed the latest virtualization technologies as required in HPC systems. So with that, let me sort of open it up to questions, Dan.
Okay. It is time to ask some questions, and I'm going to go to my partner here, Mr. Addison Snell. You're on mute.
Thanks, Dan. Thanks, Adnan. I really appreciate the presentation. I was going to ask a question from the first slide anyway. You talked about the democratization and optimization of high-performance computing for a wider range of users. Can you give me something specific that Dell does that's unique to democratize HPC to make it available to more people?
So, one of the things we've done recently is, again, with the pandemic happening and with the COVID, there's a lot of research that goes into the genomics area. So we created a reference architecture, again, in conjunction with Intel and some other partners. And we made this very easy to configure, easy to order system. And not only that, it comes with a software image of BioBuilds, which is an open source toolkit which includes all of the genomics, bioinformatics software that users can deploy on these systems without having to really sort of mess around and get everything to work. So that, in a nutshell, is one of the ways that we've really democratized that technology.
Okay, nice.
And it's available in a couple of different flavors too, right? We've got one which also works with GPUs. So,
okay.
Thank you.
Siobhan, what are you thinking?
So I have a question regarding the Dell Technologies HPC and AI Innovation Lab. So you mentioned that there's performance results and best practices that are cooked up there. Where would one find these results, and how are they publicized? Are they publicly available, or do we need to sign up to a program?
Siobhan, that's a really good question. And I want everybody to know that I didn't pay you to ask me that question. No, actually, a lot of the work that the Innovation Lab does is publicized via blog. So you can go to hpc@dell.com and you can find a lot of the publications. We do a lot of blog articles. In fact, a lot of the times when we look at the records, we can see a lot of our competitors also refer to our tunings and BIOS settings as well. But yeah, just go to hpc@dell.com and you should be able to find all of those publications.
Thank you.
Okay, nicely done. One quick question from me. You have the biggest academic supercomputer. You have the largest commercial supercomputer right now, both in the top 10. When is Dell going to go after the national labs, or are you?
So, that's we get asked that question quite a bit now. We've gone after some of those bids very opportunistically. We know where our strengths lie. And if, we know there is a chance of us winning, we go after it. If not, then we sort of, stay out of the mix. But that's an area where we've been building talent. We've been developing our infrastructure to be more effective in that space now. So I expect that to happen fairly soon.
Okay, we will keep our eyes on that, and thank you very much. Now up for the voting. How did Adnan do? How well did he present Dell's value proposition and their unique place in the industry? We shall see. If we can get that voting up there, was it a 5 excellent? Was it less than excellent? It's up to you. Vote now. As the votes are
Adnan, thank you
sliding in.
very much for your presentation.
Yes. We
It was my
muchly
pleasure.
appreciate it. Votes still coming in. We'll wait for our moderator.
Anything else you wanted to say, Adnan, while we're waiting on those votes coming in? This won't contribute to your score at all.
Well, for God's sakes, we gave them an extra
No.
minute and a half. What more is there
I
to
know,
say,
I
Addison?
forgot to start my timer, but no, again, this was a wonderful opportunity. It's always good to be amongst friends, and that's what I really like about the whole HPC group is, we've got our differences, but I think that's what makes us respect each other and love each other. So,
Very
Yes.
good.
It's a
Okay,
great
next
community.
up, I think we're done with the voting, and next
Yes.
presenter is going to be from Huawei. Morgan Malian is up.
Evening,
And
guys.
let's
How is
get-
everybody tonight?
Doing very good. How are you,
Hi,
Morgan?
Morgan.
I'm okay, thank you.
And we'll get your slides up. Start your clock.
Fantastic. Thank you, Dan.
Start my stopwatch here. Okay, Morgan, you are a go.
Okay, so if we could get to the first slide in there for me, please, Dan. Thank you very much. Okay, so I think that it's important to kind of point out where Huawei are as a business. I'm sure that everybody within the forum and the participants are aware of the press that we get. So I think what is important for me to do is kind of set the table for bigger things that will come tomorrow with some more deep dives into what it is that we do. And it's quite critical that we understand who Huawei are as a business, where we are going, and how we've kind of gotten there. You know, you can see we're a large corporate of 194,000 people. The important thing to take out of this is the number of R&D employees that we have. So we have about 48% of our employees who are R&D, spread across multiple product stacks. Obviously, HPC being included into one of those. We have a rich history in the telecommunications space. You know, we have driven our brand very strongly to step out of telecommunications into infrastructure, and then latterly into things like cloud capabilities. And how we've built up our capabilities around all of that, and how we've stacked it up to present offerings across many verticals, you know, like I kind of mentioned, across cloud, telecommunications, and then incorporating how we bring in things like the HPC components, where we've got a relatively rich history over the last 10, 15 years, and how we've developed ourselves within that space. With some great innovations that we've driven with the likes of education, geosciences, automotive, etc., to position ourselves relatively strongly as a technology leader rather than a technology follower. You know, everybody's aware of the fact that we are a global leader in the space of 5G. I'm not going to go much further than that, but it is important to understand what the Huawei ecosystem is and how it is built to have a rich offering across multiple capabilities in the entire ICT environment. If we can just move on to the next one, please. So from a value proposition perspective, you know, we obviously engage deeply with our partners. We have two of them. We have Intel, you know, who we partner with very, very strongly, and who we drive a strong message with, specifically in the space around HPC. We have some bespoke offerings that are built out on ARM capabilities as well in the HPC space. But we do have a rich engagement with the guys at Intel as well, and you know, how we can help build those infrastructures. If you look at from the slide perspective, from a connectivity perspective, you know, we do drive that the things like Wi-Fi 6 and the capabilities around 5G and core networking, where we compete very, very aggressively in the global market. And then how we integrate everything from an AI perspective. You know, AI is not just a buzzword within Huawei. It is something that we aggressively develop, that we incorporate into the broader solution set. And again, going back to that bespoke build around HPC, where we have components again, and with NVIDIA, the likes of NVIDIA and Intel and ARM, and how we again, you know, we aggressively go and co-develop solutions in order to maximize the benefit of what we're putting down. We are heavily engaged in things like autonomous driving, with geosciences specifically. In China, we do a lot around education with medical capabilities. So we have this rich offering that we continue to diversify and kind of bring out what we believe again is leading edge technologies rather than being just a following technology. Next one for me, please. Okay, so you know, we do invest heavily. We do specifically in R&D. We spend upwards of about $15 to $20 billion a year in R&D across all of our platforms, dependent on where we see the next enablement for fourth industrial revolution and the full digitalization of the global economy. We will invest heavily there, and we'll push the agenda to ensure that we are one of the global leaders in that space, rather than sort of continually playing catch up. We've built out capabilities around full stack AI. In fact, there's a catchphrase that we use internally at Huawei, as opposed to being artificial intelligence, we like to refer to it as advanced intelligence. We continue to invest heavily in that space, to evolve it to a point where we know that we can bring an offering that is relatively simple to use, easily integratable. Our hardware is we can scale it out relatively aggressively. to provide underlying platforms that will give us a good base to scale and to build on as we move forward.
Heading to the home stretch, Morgan. You're at 5.5.
Okay, nearly done. Okay. And then obviously, you know, so we continue to strengthen what we have got from a portfolio perspective, and then to drive as much operational efficiency in a company as big as we are, to ensure that, you know, we do what is necessary to enable ourselves to continue to be a market leader. And that's it.
Great.
Jeez,
good job.
5 minutes goes by very quickly.
It does, doesn't it? Yes. Let's go ahead and throw the questioning over to a Mr. Addison Snell. What do you got?
Thanks, Dan, and thanks, Morgan. I appreciate the presentation. I liked how you emphasized R&D. You talked about almost 100,000 R&D engineers, leading technology versus following technology. Your first slide had the sentence, "We invest heavily in basic research, concentrating on technological breakthroughs that drive the world forward." Can you give an example of specific basic research or technological breakthroughs for high-performance computing?
I think what we've done is that we've continued to work with global partners that have given us the ability to provide solutions and are not so, you know, limited or siloed in what they can do. So our integration and our working relationships with the likes of ARM and the likes of Intel, with SUSE as an example, and what they do around their software-defined capability in the HPC environment. So we work very closely with our partner vendors to ensure that we have a full stack of integration capability that isn't limited to, say, a single piece of kit or a single environment. And it is a continued path that we walk on to ensure that, again, that we're not being left behind.
So nothing specific comes to mind?
Look, I think I don't have a specific use case on hand at the moment, to be honest with you.
Okay.
I know that there are some significant partnerships, specifically in the education space, where the guys are doing stuff around sort of the medical capabilities with the advent of COVID and the access to remote medical capabilities and remote medical, what's it called? Consultations. Sorry.
Yeah. Oh, that's good stuff.
Yeah. So, you know, we've done a lot around that, and to enhance the ability of doctors on the front lines to access remote capabilities without having to be face to face.
Very good stuff. Very good stuff. Siobhan, what do you got?
So it seems that Huawei has various focus points in HPC and many opportunities in HPC. Would you say that Huawei has a unique role in HPC, or would you say more diverse?
No, so I think I think there's probably a bit of a middle ground there. You know, when we look at some of the stuff that we've been able to achieve from an infrastructure or deployment perspective across the globe, obviously I'm going to go back to the use cases in China, but if I step out of what we've done in China and I look at some of the stuff that we've done with the likes of VW in Germany as an example, some of the autonomous driving stuff that we've been doing with some of the French car manufacturers, yeah, you can narrow it down from there. I think that it's relatively diverse and it can be built to be more bespoke and more focused depending on what the kind of requirement is. But I think that that ability to integrate into an upper layer that is based on, I suppose, on an open source capability is something that we do pride ourselves on. We're not going to say, you know, it has to be a Huawei built for a Huawei specific use case and a Huawei specific environment. I think that our capability to extend out of that is something that is driving that messaging relatively aggressively.
Great. Well, thank you so much, Morgan. That was a great presentation. So
I've got one quick follow-up, actually. You talked a lot about AI and machine learning. Can you talk about where Huawei sees those as being overlapping and similar markets, or where is AI and machine learning distinct from high performance computing?
Ah, good.
Sure. Okay. Look, I think from the perspective of machine learning, so there could be a bit of lost in translation situation as to what we define as machine learning internally, and what we see as HPC. From a machine learning perspective, I can sit here and I can wax lyrical about the fact that we have AI integration capabilities in our storage arrays that will provide deeper learning on data analytics, as an example, versus an HPC platform that's been built specifically to cater for, I don't know, for geosciences, as an example. So I think that the overlap from there, well, there could potentially be an overlap more from a wording perspective, if I'm honest with you, as to where we sit within that space. But I think that's there has, and certainly in the time that I've been with Huawei, there has been a large focus on the development of that HPC capability, with we've got some products that will bring in machine learning and AI, some of our Taishan and our Atlas capability specifically, that will bring in stuff that will allow you to integrate machine learning with this AI. And again, we use components like NVIDIA's GPUs as part of that process, and some of our own AI developed capabilities from an ASEM perspective that we've integrated into that kit to help us blend the two together.
Awesome. Thanks, Morgan. While we bring up the voting, our audience can vote on how they felt Morgan did with the value proposition. That was a complicated question I asked you there at the end, and I don't think it had a right or wrong answer. I think it's a question of strategically, just are you approaching HPC and AI as being similar or different? You talked about it, so I just wanted to get a sense of where that fit for Huawei. Thank you for your answer on that question, and for your presentation. I appreciate it.
Yes, nicely done. So
thank you, Edison.
1 to 5. Let's rate Morgan and Huawei. As the votes roll in from the millions and millions of people watching this. And Rudy, let us know when those votes are in, when they start to tail off.
And we can start getting ready for our next speaker. Next up is going to be Matt Foley presenting on behalf of AMD. So Matt, you can get yourself ready.
Thanks.
And I think we've cleared the votes. So Matt, you can take it away. Great to see you.
Let's get our AMD slides up here. We're putting Rudy through a lot here, Addison. He's got to control all the voting. He's got to control the slides.
That's why he gets paid so much.
Yeah. Yeah, Rudy is probably the highest paid person on this entire call. But
I certainly hope so.
Okay, Matt, we have your slides, your first slide up. Let's go into the meat of it and we'll start your timer. One more slide flip.
All right. So first and foremost, similar to those before me, I just wanted to really introduce AMD to the audience because it's for some folks it's been a while. So we're not that big of a company, so 12,000 employees or so around the world. We are growing, so it's one of the reasons for sponsorship of this event is finding talent, and we are certainly a global player. We've been around about 50 years. And our mission right now from a corporate perspective is squarely in the high performance computing space. Not so much only specifically in the high performance computing market, but our view is that if we deliver high performance computing technologies at the top end of the market, if we go and compete for some of these diabolical RFPs where they do all these sorts of complicated benchmarking and complicated computer science problems, we successfully solve those, then we're able to take those technology learnings, we're able to take that with us and to use that successfully in the other markets that we've served. And that's really where we're headed forward in that, in terms of the transforming the world part. We do have, as others do as well, we do have opportunities and donations going into the COVID relief or the COVID scientific efforts as well. The first two clusters went into NYU and also Rice. And so we're moving forward on all of these fronts, but that's really what I want people to take away from it is that we're genuinely focused on HPC from a corporate strategy perspective, in that because we believe that having such a focus brings us more benefits in the broader markets that we serve. So next slide, please. So, and the next slide has a statement that will be true for a while, but probably not for all time, because AMD is Intel's primary competitor in CPUs. We're also NVIDIA's primary competitor in GPUs. And we've been, for a while at this, we've had both. And that's been an exciting position for us to be in. And we're starting to really leverage the strength of both of those now. And as you've seen, and as Addison's presentation showed as well, there's a lot of drive within the industry to combine these types of functionalities at the component level like we do. And so we're excited about that. We are pressing forward with this strategy. We believe that it's been successful in terms of winning the exascale opportunities, both at Lawrence Livermore National Labs as well as Oak Ridge National Labs. And we see continued appetite really for this combination of CPU and GPU technology as we go forward. So, and speaking of those combinations, I'll go to the next slide. So, and really this one is, kind of, and now for something completely different, because what I wanted to share here was this is what AMD is doing about the problem. And this Infinity architecture is underlined by the Infinity Fabric, and that is a cache coherent bus that if you've seen the inside of an EPIC CPU, you'll notice that it's a multi-chip module. And so the Infinity Fabric is what connects all of those chips together. An external version of that Infinity Fabric is also what connects the CPUs together. That's the cache coherency bus in a dual socket system, for example. And then if we go to the next part, that same cache coherency bus is also what we're using in the GPU space. So the Infinity Fabric is also what ties together Instinct GPUs as well. And so if you have to ask the question, we use it inside the CPU, we use it between the CPUs, we use it between the GPUs, what's the next step? Well, from a hardware perspective, the next step is to get cache coherency between the CPU and the GPU. And the reason for doing that is, of course, for performance, to try and get the performance out of the system. It makes it easier to program, it makes it more accessible to the consumer, makes it more accessible to the researchers and the users. And so I'd like to tell people the story of AMD. A lot of times you can tell it in a fairly simple technology structure. It's this Infinity Fabric. First you innovate in packaging, then you stitch these things together, then you stitch the GPUs together at the component level, and then tie everything together. And that really makes a difference, because for us, having control of both sides of this, it allows us to better leverage the two together. Vector processing in the GPUs, general purpose processing in the CPUs. It allows us to save die space, if we want to put functions somewhere else. Where do you put high bandwidth memory? All of those kind of questions, we have the opportunity to answer them, I think, in creative, interesting, and different ways. And I see from my timer, I am almost out of time, so I will go ahead and stop there. But thank you for your time and attention. It's certainly a pleasure to be here with you guys.
Great job, Matthew. He comes in right under the wire. Highly appreciated. So, first question, let's go to you, Siobhan.
So interestingly, I saw in a recent promotional video about the MI100, AMD claimed that it's the world's fastest HPC accelerator / GPU. May you comment on this claim?
That's based on the floating point matrix performance of floating point 64. So it's over 10 teraflops. It's in fact 11 and a half. And there's a slide in the GPU deck that shows that the #1 system in the top 500 in 2000 was, I think, a 12 teraflop system. So it used 6 megawatts. Now we have this in the card, but it's based on that. And the card itself is really focused at more at HPC workloads. It's really single and double precision floating point is the sweet spot for it.
Good answer, Addison.
Matt, I liked your very bold slide saying that AMD was the only company that had both high performance compute and high performance graphics. That pill might have been a little easier to swallow if it said the only one with high performance CPUs and high performance GPUs right now. But that notwithstanding, I was interested in the fact that Ryzen was on that slide on the CPU slide, on the CPU side. Can you talk about Ryzen a little bit in the context of high performance computing? Maybe is that with the workstations and Raven Ridge? Where does Ryzen fit into the portfolio?
So Ryzen does fit in terms of the workstation, but also the way that we compete across the broad spectrum that we do, even though we're relatively small compared to our competitors, is that technology leverage. So the same cores are going into Ryzen that go into EPIC, the same graphics actually that go into the APUs as well. And so if you think about the broader vision that I had at the end, where you're tying all these CPUs and GPUs together, we've already done that at the client level in terms of APUs. From an HPC or high performance computing perspective, the place where this really comes home is actually in the workstation space. So we've provided now some significant workstation horsepower here. Also, you can use the GPUs in the workstation to better prepare your code to then be deployed on the larger clusters.
Thank you.
Nice question. It seems like to me that with your interconnect, are you kind of edging towards big SMP down the road?
That's a good question. The thing about it is how many cores do you really need, right? Because once you're at like 64 cores inside of a CPU, do you really need to go to a 4-processor system in terms of those SMP, big SMP kind of nodes? So from our perspective, and from looking at it here, we get into the problem of failure domains if you actually get to too many cores in a system. That doesn't mean that the future is written in stone. There's certainly structures inside of there in terms of how those infinity fabrics can be arranged and organized. But as of now, it's 2P for us.
Okay,
Matt,
good.
to be fair, I should ask you the same follow-up question I gave Kirti earlier, but asking it from the other way around. You're banking a lot on ROCm as your development environment, particularly with tools like HIP for moving codes into ROCm out of CUDA. Can you talk about ROCm in context of other competing development environments like one API and CUDA? So
from our perspective, the objective from our software stack is to be open. So the software stack is open source. It's available on GitHub. And in terms of how developers weave those together, or how we come together as an industry to solve particular problems, we've certainly been willing to participate in all of those types of initiatives in the past, and will continue to do so. In terms of specific product directions, or do we have an agreement, or those types of things, I don't know those particular answers. But in general, what I would leave you with is that the strategy going forward for us, and the strategy in our software, is to be as open source as we can possibly be, so that we can then give the users as well as ourselves the utmost flexibility.
Thank you, Matt.
Nicely done. Very good. Very well done, Matt. Let's go ahead and vote. So we can bring
Matt,
that
I appreciate the presentation. As I said in my talk earlier, a lot of this is really the high dynamics area of the HPC market right now, with the development around CPU and GPU. So your answer around ROCm, I particularly appreciated while these audience votes come in.
Yes.
Thanks.
And speaking of which, I believe next up on our slate is going to be NVIDIA. And we're going to be hearing from Timothy Lanphier, and possibly additionally from Gilad Shainer for NVIDIA. We're going to hear from both of them to combine the GPU perspective and the interconnect perspective on InfiniBand.
So we're going to start with Gilad, in fact.
So a little tag team on this.
Yep.
Let's get the NVIDIA slides up.
It's all about collaborations then.
We're going into high performance parallel computing here. We're going to have two guys split the 5 minutes. Let's see how they do. And Timothy, that's brave, letting Gilad go first when you're sharing your 5 minutes.
I was just going to say.
I did think that.
I've heard Gilad go 5 minutes before he gets to his first comma.
Yeah, Gilad. 5 minutes to Gilad is like the smallest granularity I believe you can get out of him in a presentation.
Yeah.
All right, here it goes.
First, you need to have a clock that you can measure 5 minutes. So far I measured 57. But it's something else.
Here we go, Gilad.
Okay. So we'll try to save with a number of words on the slides and actually try to make it simpler. 10 years ago, scientific computing primarily consisted of first principle simulations and basic visualizations in a centralized supercomputer. Today, researchers are fusing traditional simulations with deep learning, big data analytics, and streaming edge computing to solve the mysteries of the world around us. Higher fidelity sensors, like the square kilometer array, for example, and the ability to run large-scale simulations have resulted in an exponential increase in scientific data that needs to be processed for insight and requires scientific computing to be great at edge streaming problems and data analytics. And of course, these demanding workloads rely heavily on the networking layer to meet the application performance thresholds, to connect all the components together, and to accelerate AI and HPC applications. Next, please.
So I'll take over here. So I'm sure that everyone on this call loves technology, but in the end, technology is not the end goal. So the vision of NVIDIA is to enable scientists to do their life's work, and indeed to accelerate the computing so they can complete their life's work within one physical lifetime. So NVIDIA is becoming very successful in this area, and we're seeing good acceptance of the NVIDIA technology in the Gordon Bell Prize. And I'd just like to talk about a couple of those that came forward that were in the final round of the Gordon Bell Prize this year. First of all, the Square Kilometer Array, which I'm sure is a project very close to the heart of the people in South Africa. This was an application which was really testing the ability to move and manage the large amounts of data that the SKA is going to produce. But it also required a very large computing aspect to this application to generate simulated data similar to what the telescope itself will produce. There was a special prize awarded for research into COVID, which was shown on the far right-hand side of this screen. And this is the largest molecular dynamics simulation that has ever been done. And the goal here was to work on to simulate the COVID virus. And also we should say that the performance was greatly enhanced by using artificial intelligence to understand the behavior of some of the molecules. And we see frequently now in these large-scale simulations, the coupling of artificial intelligence and traditional scientific computing. So back to Gilad for the final slide. You're muted, Gilad.
Yeah, we're going to make it in less than 5 minutes, looks like. So there is nothing like building one in order to really understand the challenges and how to design the next generation. And it's great to have be able to put our hands on a number 5 top 500 supercomputer system, which include almost 5,000 GPUs and almost 5,000 HDR 200 gigabit per second InfiniBand nodes to deliver not just one of the leading supercomputer and us be able to create a recipe that enable people to build something similar in a few weeks, but also to develop our next generation of technology, understand what are the main issues from an application perspective, from technology perspective, in order to build the generation moving forward. So it's great to have a system like that, and we're looking forward to actually build even larger systems in the future. And with that, I think we are done. And you owe us a minute, right?
We owe you 24 seconds. Nicely done. Very nicely done. No one would have bet on this. We couldn't have gotten any action on this. So Addison, fire up a question.
Thank you. All three of your slides made specific mention of artificial intelligence. So I'm going to ask you a similar question to what I asked Morgan from Huawei earlier. To what extent do you see AI and machine learning as being a distinct market from high performance computing versus same market or different workloads in the same environment? How does NVIDIA view these as being together or separate?
Dave, do you want to take it and I'll add?
Oh, okay, I'll say something first of all. I think that the market for AI, and let's include also data analytics, is larger than HPC and certainly larger than academic HPC. One of the places where we are driving forward is in the enterprise. Enterprise computing, they require large computing systems, but it's far from traditional HPC. And data analytics, understanding the streaming of data from the edge coming into the enterprise is a place, I think, where there's going to be additional growth for this AI market.
Yeah, and I would add one more thing, by the way. HPC and AI is being fused. There is no doubt. HPC or simulations, traditional simulations create so much data that you can use in order to have the computer create algorithms that help you to make those simulations even more accurate. So, you know, that's how the future is going to look like. You're going to have those systems that run the simulations and run AI, and they're going to completely be fused together. And people that understand that, they're building systems that support both. And if you look on most of the large systems being deployed or the new systems, they are completely including capabilities for both AI and simulations, because that's the future.
So, sorry, I have to have a follow-up on this. Gilad, you said they're being fused, and Timothy, you said that AI is bigger than HPC. Is your implication then that HPC is a subset of AI and data analytics, so all HPC is AI and data analytics, and not all AI and data analytics is HPC, or vice versa?
Clearly, to do AI well, you need big computers. It's an application of HPC.
Okay, thank you.
Okay. Siobhan, go at it.
So I have a question. So do you have any examples where you've used your simulation capabilities, your visualization capabilities, and your AI capabilities all in one to solve one problem? Do you have any examples of that?
In fact, we showed one on the slide. So the COVID simulation was all three combined together. So there was a molecular dynamics application that was doing the modeling. There was a molecular dynamics visualization package that was looking at viewing and rendering the application. And also AI was used as a means for accelerating that computation by learning the behavior of certain groups of molecules and feeding that information into the simulation.
Thank you.
Nicely done. On the GPU side, the accelerator side, I can count at least 50 other companies that have products in the pipeline that are coming for AM or for your GPU dominance, and to get a piece of that very large pie. This includes traditional accelerators like FPGAs and completely new spins on silicon. How do you feel this competition is going to end up? How are you going to stay on top?
So first of all, it's good that we are the benchmark. You know, when everyone's comparing against you, that means you're the one to beat, which is
a good place to be.
In. If I may give a slightly nasty answer to your nasty question, I would say
I would appreciate that. Thank you.
I would say put up or shut up. You look at the things like the MLPerf benchmark. Who is providing, submitting performance data across the board for that benchmark? And when people have something that they can actually show, then we'll talk about it.
Okay. Then let me ask you this bigger question. What keeps you up at night? What do you worry about?
Do you want to say something, Gilad?
Gilad sleeps like a baby.
No, first, First, I didn't know that Dan knows how to count to 50. That was a surprise. I thought you kind of end in 10, but
I had some help.
I think we focus completely on driving our technology forward. That's what we focus on. What keep us late at night? It's how to solve the challenges that will enable the next generation of GPUs or networking, how to enable the next capabilities from an application perspective. We built the Selene system in order to explore things at scale, explore where things are going to the edge of things or capabilities, and then trying to see how we can build the next leading or bleeding edge technologies to drive the next level. Typically we don't look sideways. We focus on the technology itself, and we're trying to beat ourselves actually from generation to generation and to build the next generation. That's what keep us awake at night.
So Timothy, would you say the same thing? You don't look in the rearview mirror at who might be coming up behind?
I think it's always important to look at the competition, but you know, we are a company that moves as fast as we can. We have a CEO who drives the company forward, and there's no chance to relax when you work at NVIDIA.
That I have heard. That I've heard. Any other questions, Addison, Siobhan? Or should we vote?
We're at time. Yeah, let's bring up the voting.
So how did the tag team work? How did they do?
Excellent. And while this voting is going on, I would like to thank not only Gilad and Timothy for doing this, but for all of the vendor sponsors for stepping up into this interesting format. These are the sponsors who make these conferences possible. And yes, I'm very grateful that the companies do that so that we can have this. I love the CHPC conference, and it's only natural that any sponsoring vendor would like a chance to give their product pitch. We've done this because we found, in my experience, when you get 6 consecutive half-hour-long product pitches, that's often a signal that everyone leaves the room, and that's no good, because you know, I appreciate the presenters and the sponsors, and I want to hear the information. The fact that they've all stepped up to this more engaging and challenging format is very sporting of them, and I really appreciate their participation. So those votes are in, and we're going to go to the last presentation of the session, which is going to be from Altair with a presentation by Bill Nitzberg. Take it away, Bill.
Let's get Bill's slides up on the screen.
All right, thank you very much. Can I
festive shirt.
This is the first time I'm
appreciate
Can
that.
You hear me okay?
Yes, we can.
Okay. I was just going to say, this is the first time I get to come to South Africa, and I'm really happy to be here, and I really wish I could be here. But anyway, good morning, good afternoon, good evening, everyone. You could go to the first slide. Let me just say that Altair believes high performance, one more slide, there we go. High performance computing improves people's lives. I believe high performance computing improves people's lives. It's not just about building better products, which we do with this stuff. You know, making sure my cell phone doesn't break when I drop it, which I keep doing because I'm at home now. Somehow you break more stuff when you're at home. But also, you know, doing the bigger things in life, predicting where hurricanes will land to get people out of the way. And of course, really important now, doing a lot of medical research to get us out of this pandemic. We focus, okay, so at Altair, that's what I believe, and that's sort of the why of what I do this stuff. But at Altair, we build software. So we've heard a lot about hardware. Let me tell you a little bit about the software and where we focus. We focus in 3 areas. So one is we try to make HPC more accessible. That means engineers and scientists touching high performance computing without actually having to touch Linux or IT or, you know, type SCP and as much and figure out what the job control language is. Being able to go to both on-premise clusters and clouds in the same way, thinking about science instead of thinking about information science. Although I'm a computer scientist, I like that stuff. But, you know, like I said, one of the things I like to say is we like to protect people like you from people like us. The second thing we focus on is optimizing HPC, and that's making HPC resources, clusters, clouds, software licenses, file IO, faster, more efficient, letting you run the right work, and letting you do it at the minimal cost. And the third thing is we focus on letting system administrators control HPC. And for that, the one thing that I think about when we're thinking about how we help you control HPC is, if you're a system administrator, the last thing you want to have happen is your phone ring in the middle of the night when something goes wrong. And so we focus our technology to try to make things more robust, more scalable, more automatable, and more visible. Next slide, please. And that's weird. All right, well, while they're getting the slides together, I'll say that we're in the PBS, so the software that Altair delivers, there's a slide after this one, it's okay. The software that Altair delivers, that I work on, is PBS Works. PBS Works is focused broadly across sort of what I think of as 5 core areas, which are fast scheduling, exascale, security, user experience, and efficiency. And in those spaces, we're doing that almost every day, almost one back. There we go, is the top part. We're doing those core things, I'm doing them every day. We're thinking about them all the time. We're spending our time there. We believe that we have the world's fastest scheduling system for job scheduling and workload management, millions of jobs, almost tens of millions of jobs per day. We're also working at exascale. You may have heard the Aurora project at Argonne National Lab is using PBS as the base scheduler. Although that doesn't show up in all the marketing because, it's of course the natural thing to do, I think. Anyway, and for 2020 and maybe moving forward into 2021, maybe 2022, we'll see. We're focused on sort of 5 key areas in high performance computing of where we're pushing our software forward. So one is further scheduling, bringing together high performance scheduling, high throughput scheduling, scheduling of AI stuff. Number 2, in cost, and we haven't heard a lot about cloud, but cloud actually takes cost from this background thing where you spend money once every few years to something where you're spending money every minute now. And so cost becomes super important, and we're actually elevating that to a first-class citizen. And then I just mentioned cloud. Ecosystems, so not only how you plug in our software into your system, but making sure that if there's something you want to plug into in the broader ecosystem, not just whether that's cloud or whether that's storage or whether that's that, we have the right APIs and the right interfaces to support that. And then finally, kind of bringing together more of the AI data analytics stuff into the whole ecosystem. And we're spending a lot of effort, I should say, a lot of our focused effort in that broad space. And if you go to the next slide, and I'll just say, so what do we offer in this space? So we have a whole product suite that I think sort of spans a nice end-to-end piece of the high performance computing space, from workload management. And I'm sure I'm going to get a question about this, so I won't even say any more about that with a lot of tools. HPC usability, especially for clouds. One of the things that we actually can have demonstrated now, I can say this, after a recent acquisition, is we've actually built a system that has scaled up and run 1 million cores on a cloud. But we've also added a bunch of license and IO scheduling and telemetry tools to the suite. And then finally, we have one of the few high-end dependency analysis tools, FlowTracer, which is actually a tool that allows you to take millions of dependent jobs and hand them off in a system in an automated way to get something done really fast. And I'm going to stop there because I had started a timer, but my timer stopped. So I don't know if I'm out of time.
You're good. You're good. We gave you a little leeway because of the slide problem. Good job. Very interesting stuff. Let's go to some questions. Siobhan.
So maybe discuss some of the ways that your technology enables scientists and engineers to do real work. So could you expand on what a hypothetical engineer would go through to use your technology, and how would this compare to the traditional way of doing things?
Nice.
I think the best way to do that is to describe what I think of as a really innovative thing we've done. So we built something called Access Desktop, which is a tool that you install on your Windows desktop, basically. It actually runs completely in the background. As an engineer now, once you've installed that, you can do your normal workflow. So say you're running something like a structural optimization tool, and it's got an input file, it generates some output, whatever, and you want to actually, instead of just running it on your workstation, on your Windows desktop, you want to submit it, say, to your backend on-prem cluster or off-prem cluster. So Access Desktop actually integrates directly with Windows inside a File Explorer. You can go to an input file, you can right-click, it will actually pop up just an extra little couple of choices on that right-click, besides copy and delete and stuff, and it will say process with. And you can actually say process with, for example, OptiStruct if you're doing structural optimization using Voltaire tools, and then just click that button. Behind the scenes, that will actually grab your input file. It'll grab include files from your input files automatically. It will copy everything, upload stuff to your cluster or cloud. It'll submit the job. It'll run the job in the background. If you want to, you can actually click through and see your job running. You don't have to. You can actually see nothing. It'll create a little file on your desktop. Sorry, a folder on your desktop, which will actually tell you like it's uploading files, it's running now, it's downloading files. When it's done, downloads all the files. You just have your output file. You want to run 100 of those, no problem. So it's really almost 100% invisible HPC.
That is impressive. Siobhan, you have a follow-up?
So would the engineer have to install the software themselves, or do you have like a catalog that they could choose from and it comes pre-installed? Or?
We're actually working on helping you pre-install it when you have HyperWorks. So HyperWorks is the other, I work in the HPC part of Voltaire. There's actually a big mechanical computer-aided engineering, manufacturing part of Voltaire. If you install HyperWorks, we're working on actually installing this stuff automatically for you. But you would have to install it by yourself if you're just an engineer and you want to actually take advantage of this on your desktop. I mean, obviously, if you're in a big engineering firm, your IT department will install it for you.
Thanks.
Good questions, good answers. Addison.
I was going to ask things very similar to what Siobhan already asked, which speaks well to his future as an analyst. I can do a follow-up on that, or I can defer for now to you, Dan, if you've got one you want to grab.
I've got one I want to grab. Let's talk where the rubber meets the road. One of the biggest thing that HPC users look for is performance. How do you argue against someone that says that your type of software is overhead? How do you show them and prove to them that there's real value in this?
So our software, if you think about scheduling software, even if you think about the Access Desktop software itself, we're not getting in the way. We're completely agnostic to the HPC system that the HPC algorithm that you're running, whatever application you're running. So we're going to set up your process, and then we're going to get out of the way. We're not actually anywhere in the inner loop of that. I think where we deliver a lot of value is if you have 1,000 design of experiment runs that you want to run, or say 10,000 or even 1 million, you can hand them off to our system, and then we'll make sure they run as fast as possible in the right order, despite faults and failures, even while you're sleeping. And so in terms of getting more work done, which I think is the key to what we all want to do in HPC is I spend a lot of time thinking about return on investment and saving money, but really the key is, hey, get my work done, get it done faster, get it done sooner. And that's really where our sweet spot is.
Well, that's the thing. Getting the job done has an ROI and TCO impact of its own. Getting it done faster, that is very hard to measure. Addison, back to you. Any thoughts?
I just really appreciate having a software-oriented conversation. We've talked a lot about the democratization of HPC, and from our research, what we found is that as new users come into HPC, it's often at that intersection from the desktop or workstation into the entry-level clusters. And Altair is an interesting company in that, Bill, you were presenting primarily the middleware side, but it's the only company I can name that has HPC HPC middleware and CAD/CAM software and CAE software all under the same umbrella. So you're kind of at that intersection of all of those things. So I guess my question then is, do you see an integration of those growing where we're going to see more of an integration of HPC middleware, CAD/CAM, and CAE that's cloud optimized all in one product?
Absolutely. I mean, I think you could have just given that part of my presentation for me. I didn't actually talk about that so much. One of the things that I think is really neat about actually owning or working in a place that has such a broad spectrum of where we sit in HPC. I mean, we even actually have a piece of hardware that we sell that actually combines all this stuff. So it's really a wide spectrum, is that we can actually combine these things. And I didn't talk about it in what I said, but we also have actually a side of the business that does artificial intelligence and data analytics. And we're actually putting all those things together in the next version of HyperWorks, which is the premier, software tool set that we deliver for our mechanical and basically the engineers doing the real work. We're baking in some of this stuff that I said. So we're baking in this Access Desktop stuff that I said. So you won't even necessarily see the connection to HPC anymore. You might not even see the connection to the AI anymore. You're going to be inside of a screen where you've got, your new, we'll go back to a cell phone here. You're designing a new set of glasses and you want to make sure that they're working and they're not going to twist or something. You're going to exactly. You're going to push a button at some point to, do all the optimization for when they're dropping. You're not going to know that half of what you've done is actually done by AI to figure out, which optimizations to run. The other half's going to run on the cloud. Some stuff's going to run locally. It's just going to happen. And we're not even going to, I really hope this doesn't happen in my lifetime, but you're not going to notice that HPC is there because HPC is just going to be baked into everything. It's going to be, something we don't care about anymore.
We'll always care.
I have my own definition of HPC, which will probably make it not go away.
I'll hire you as an analyst too. All right. Well, thank you, Bill. I appreciate the perspective. We're going to get to the voting. That was the last of our presentations. We do have to get the voting in, and then we'll reveal who was our top vote getter from all of these sessions. Bill, you and I have very similar models on the glasses as far as they go. I am looking
throw
forward.
mine up as well.
Yeah. I also wish that we were live in South Africa. It's a long flight from the San Francisco Bay Area and well worth it. And I look forward to participating again in person, hopefully next year. In the meantime, I'm looking forward to getting to any conference where me giving a presentation does not involve me wearing my reading glasses. I'm fine looking farther than 2 feet away. But hopefully we'll get back to that all pretty soon. Dan, any closing comments or actually I want to go to Siobhan first. How was this participating in your first vendor Crossfire and what did you think of the student cluster competition?
Well, participating in this first Crossfire, I think it's a very unique idea to kind of sell products, but in an interesting way. Like to allow people to have the stage for a certain amount of time and ensure user engagement. So I think that's quite nice. And on the student cluster competition sides of things, I think before this year, I had no idea what HPC was. I was into software development, and that's as far as interconnected as I was to it. But it's actually, I realized it's a whole new world, and it's actually quite amazing. And you don't realize how much HPC is actually taking part in the world.
Yeah. And that's kind of a universal thing that we hear, particularly in the South African cluster competition, because 98% of the students are brand new to HPC, and they put together a great program, Addison, to bring them into the industry.
Absolutely. And Dan, you've been heavily involved in student cluster competitions as well. I really admire that, and just a huge amount of gratitude and appreciation to Happy Satolle and Werner Janssen van Rensburg for the program that they put together here. And
don't forget David McLeod, who's been the coach. David McLeod, who's been the coach of every South African team. And without him, I don't know that there would be a South African team. He's done so much. So
and meanwhile, the results are in, and we have a winner of the highest average score of all of the presenters. The trophy, we're going to need a pair of trophies because it goes to NVIDIA.
Whoa!
So congratulations to Timothy and Gilad. You shared the spotlight quite effectively and got top marks from our audience.
And came in at 4 minutes and 34 seconds, I believe.
That might have been factored into audience's ratings. We don't know for sure, but I would like to go back to what I said before about appreciating all of the vendors stepping up to this format. And we can see on our end, the participants, people really hung in there for all the vendor presentations, which is why we do it in this format. And I appreciate the sponsorship to keep events like this going, particularly in a trying year. We're doing all this virtually from our desktops, and there were some hiccups with the slides. Rudy did a great job behind the scenes. Thank you, everybody, for doing all of this. I appreciate the hard work.
Absolutely. I second all of those comments. And thank you all of the people out there that have been watching. I believe this is the last event of the day. So
that's true. I don't know if we pass it back to Werner for any closing comments for the day, or if we just dismiss everybody. Is Werner here in the room with us?
I believe the bar is open.
I don't see Werner here, so I will just dismiss everybody. Yeah, exactly.
Yes.
The bar is open. I wish we'd all mingle together, but thank you for the completion of the first day, and welcome again to the CHPC National Conference. Thank you.
Thank you. And I've been drinking here already, so we're good. Thank you very much.
Thank you.
Thank you.
Thanks, everyone.
You are free to leave the meeting.
Well done, Shab. Oh, he just rang off. Okay. Well, he did a great job.
Yes.
Addison, I see we've got a few last attendees logging off, but I'm going to close the webinar for the evenings. Thank you very much. I thought that session went brilliantly.
All right, thanks. Yeah, that was a lot of fun. Dan and Siobhan did a great job. The panelists did a great job stepping up to that format. I really am quite appreciative. So, and thank you for all of your work.
No, of course. Thank you very much, Addison. And then I'll chat to you soon.
Yes, we'll talk to you soon. Thanks.
Awesome. Have a good evening. Oh, a good day to you.
Yes, just starting.
Bye-bye.
Thanks. Bye-bye.